Typhoon became a bus. Yeah. So, no direction. スーパーセンターから二宮に集合まで。Yeah. It's very tough. But it's very nice. Yeah, that's right. The weather is much better than last time. It was cold last time. Screen sharing. Yeah. Okay, so, おはようございます。おはようございます。Okay, so today is the second day of Typhoon seminar. I think Dan will continue to talk about today. I think you will more focus on hazards. Okay, right?
Not just, I'll start actually, that won't be a super long part, but we're talking about some simpler, more practical models, and then actually we'll go back into, if we have, depending on how much time we have, the size expansion stuff, which is a mix of some observational applications and also some serious theory that I'll only go into. So.
We totally enjoyed the talk yesterday, so let's welcome.
Great. Well, thank you all. Good morning. So thanks for coming for day 2. So I guess day 1 was worth it, or made it worth it to come back for day 2. So I appreciate that. Yeah. So today I'm going to start off kind of starting again on the hazard side, but just show you some applications of the wind model that we talked about yesterday. Yeah. So just give you a flavor of some applications some of my colleagues have worked on that I've been a part of. As well, just showing how you can apply a simple wind model to model some of the hazards, and then I'll talk about the minimum pressure as well, both or in the context of hazards here. So yeah, so we'll be talking about hazards, damage, risk, whatever you want to call it, and this is just a little bit more to motivate again the utility of some of these meteorological tools or physics-based tools. So. Wind surge and rainfall, and I'm going to talk about minimum pressure, and maybe you guys will have some thoughts on that as well. So yeah, just want to show some applications. I won't get into the details of these, but just showing you some of the things done with my wind model that we published about 10 years ago, the one I presented yesterday. And so this is a paper just looking at a very simple thing. And some of these things you don't have to use my wind model, at least in this case, but just a colleague of mine, Renja Jing, just published a paper looking at exposure to tropical cyclone winds and used my wind model for that. So we're using it inland. So it's a very simplified way to estimate exposure. And so again, I'm not focused on any of the details here. You can just see, I guess we have Japan. Apparently all of Japan is pretty high risk, probably not surprising to you all. But yeah, this is one thing where they just were able to look at or use the wind model to simulate the wind footprint. And then in this case, they were actually looking at demographic information. So how wind exposure or how wind hazard exposure varies with like demographic conditions across populations. So a second thing that I think is a lot more exciting, that's very much ties into everything we talked about yesterday, is has anyone in here run storm surge simulations ever? No, okay. So we have models for storm surge, which they just model the ocean. There's some simple ones and some more complex hydrodynamic ones. And so the most sophisticated one that's commonly used is called AdCirc. And it's just what it takes is the forcing is the surface wind field. And so I guess I should have put a schematic up here, but I mentioned before how surge is just wind. You're just literally blowing on the water and it pushes it around. And so you could simulate that in the full 3D physics of the upper ocean, and along with the bathymetry. And so to force it with the wind field, you can give it my wind profile model. And basically, if you have the intensity, and then we said you need a size. And so what my colleague, this is Avi Gori, who's in civil and environmental engineering at Rice University. Now, she took the wind model and then pulled out the radius of something like 6 meters per second from reanalysis. So basically matched up the tracks from best track with intensity and then actually matched it up with ERA5, which you'd be surprised is actually, for the far outer wind field, is actually can actually capture the outer wind field of the tropical cyclones. It's not going to get anything anywhere farther in. Reanalysis is to coarse resolution, and it's also not really assimilating data relevant to getting the inner core right. But all I need is one size metric. So in her case, she took one pretty far out, and it gives you a wind field where you have intensity and size varying along the track. And so she did that for all United States landfalling hurricanes. And you could simulate the entire storm surge field from every hurricane that made landfall and along the coast, and then pulled out the peak storm surge and compared that with observations. And so this is showing the results here. And again, I don't want to get too into details. I'll just say kind of overall, this is broken up, as you can see, by different regions along our coastline. And in general, it does a remarkably good job. Like we can re-simulate peak storm surge going back. I think we went back, went all the way back to the 1950s even, and get a pretty good estimate of the peak storm surge from historical storms, just from intensity, reanalysis, outer size, and then my wind model. And so, so that's, I think, actually something, it's sort of I should say actually here, this is something where, you don't have to use my wind model, but the physical basis is really nice, and actually in separate work. So this was I worked with Ning Lin at Princeton, who's a surge modeler, and so some of the members of her group have also tested sensitivities of storm surge simulations and consistently find our model to be the best one. So I'm not saying it's the only way to do it, but it's really nice when you have a really good wind model that you believe in. It turns out that if you then to go the next step and say, well, let's apply that to simulate something that wind creates, a particular hazard, and it does a good job. That's I think another level of credibility to say, hey, this really works. Like this is another, maybe it's semi-independent test of the utility of the wind model. So that's something that I think is very cool. And then a second one, which I'm happy to get into some of the details on this. So Carrie Emanuel has created a very simple in that it's an analytic rainfall model forced by a time-evolving surface wind field. And so I'm not going to present on that, but it basically predicts a topographic vertical velocity. Actually, did I put a slide in here? Yeah, like it predicts vertical velocities from different things that cause vertical motion. And so if you know and then if you give it, say, a relative humidity and a surface temperature, you can predict the vertical velocities from topography, from baroclinic forcing, from friction, from changes in the vortex structure, and put that all together, and it actually predicts the rainfall distribution. And so there's been case studies so this is Ping Lu, who was also in Ning Lin's group, but was part of this paper as well, did some case studies. But this is a case where, again, this is Xi et al., also from Ning Lin's group. I was not part of this, where they, again, took all the historical hurricanes that made landfall and looked at, or actually I think just all the hurricanes in this case, and looked at the climatological precipitation, mean annual precipitation from hurricanes. And so this is what they got from observations. This is satellite-based observations. And then this is rainfall simulated from the model, where the wind field that forces the rainfall model is my wind field model. And this is one that if you use this is where the specific details of the structure of the wind field are really important, actually, because rainfall depends a lot on changes in relative vorticity within the structure of the wind field. So if you'd use other models, they actually do a lot worse. I guess I should have put that, what it looks like with a different model. They also tried the Holland 1980 model. So anyways, this is just another case where it does a surprisingly good job. I will say this is why I don't want to go into Carrie's models. There are some tuning parameters that aren't very clear exactly how they're tuned, but it's still meant to be. It's a physics-based rainfall model. So this is a place, again, where you can do, to me, a shockingly good job. Because, I mean, this is an axisymmetric, well, it's not an axisymmetric rainfall model, but it's an axisymmetric wind field applied to in the rainfall model. And so as we've talked about rainfall, even for Milton, as we talked about before, all the rain was on the left side. Like, there's a lot of other things going on. Although this model tries to capture some of those baroclinic effects as well. So again, I don't want to go into detail. It's not my model specifically, but it's just a place where applying this wind field model, you could actually simulate rainfall, even hazards as well, with a decent level of reliability. So again, if you do have questions, ask. I'll try to fill in. These are just kind of some higher level things. There's another step we went. This is again with Professor Avigori at Rice. Is to actually do it all together. Is to simulate. What she did was to simulate wind speed, storm surge, and rainfall, all with these models I showed before. I'm using my wind profile model, and then actually link that with county level economic damage that we have historically from hurricane landfalls. So these colors here, reds are higher damage, This is from 1996 to 2020. And then doing something incredibly basic, which is just to do it's a Poisson regression model, a log-linked linear regression model, to basically say, can we predict the economic damage from wind speed, storm surge, and rainfall as a function of each of those. And there's a lot of noise in this, but like overall, this is just showing you a sense of this is the log 10 of the model damage versus the observed. And I think in this, at the end of the day, this is aggregated across, it's total aggregated across each storm. So, and you get, something, economic damage is a lot more complicated than a lot more things than just physical variables going into it. But we can even do an okay job of predicting variations in economic damage from hurricanes, just based on these, like basically physical modeling of these hazards, which comes back to using the model. So this is just, I think this is pretty cool. It's just, a way to really go all the way from the physical modeling. At the end of the day, damage is caused by hazards that are driven by meteorology. So it's trying to actually link that all the way through, which is pretty amazing.
So does this model consider the population of each county?
Yeah, so that's the thing. So it's no. I'm trying to remember now. I want to say that no, I want to be careful here. I think she did. I helped on the physical side. Is that I think there was no, that's not yes, it does. The model is, I should be careful here. This is the physical part, but then there's also just an exposure part. So so it's both of those together. So yes. So if anything, you could almost think of it as like the ratio of how much damage happened, the fraction of economic, of whatever, exposed economic assets that were damaged. You can think about it that way. So, is it good? Good question. This is where you're going to get into the details of the data. I assume it is, because that's usually, my understanding is that's usually what we have for numbers of economic damage. Historically, the total damage has just been assumed to be twice the economic damage, like double it, which is a very crude assumption. So I believe it's based on insured numbers. So there's all sorts of caveats and reasons to be skeptical of how well that holds up, but that's the best we have. So yeah.
My question is about the application of your model.
Yeah.
Operational purposes. So I understood that the model is useful to simulate optimal cycle of the past.
Yeah.
For which we have the analysis test track,
Right.
and so on. Do you have any thought on the application of the model?
We'll get to part 4. I think will be where the next after this part, I'll talk about a new model and new simpler ways to do it. Is because I think at the end of the day in operations, you have a lot more information often, and I think it's something I hope to hear what your thoughts are at the end, even is like, based on, like, I've tried to go as simple as possible to say, I just want one size and one intensity, but then in reality, maybe you have many data points on size and structure and how you could use that. And I think there's interesting ways that the model could be used to integrate multiple different pieces of information. So, and then of course the other thing is like, I'm in the real world, everything is not symmetric. And so I think that's another part. I don't know. Yeah, I have some thoughts, but I'd love to hear also from you all on that. So yeah, but hopefully the next section, it'll be a little bit more practical application, trying to think about how to use it in practice. So yeah. All right. Since all driven by my window. Oh, wait, oops, I switched the order. That's all to come back to that point. Okay, so that's the hazards. So this is also relevant because hopefully, so we've talked about pressure a little bit. I'm going to talk about it a little more here, and I'll talk about it more specifically in the next section. Is independently along this front is that there's a strong link between the minimum pressure and damage and risk. And so I want to bring this up. I'm not quite sure if this happens for you all operationally here. I know we've talked quite a bit about how JMA approaches central pressure. So in the US, it's always maximum wind speed, or categories are maximum wind speed. That's the WMO standard. But this is something that happens a lot. And this goes back to 2005, but this happens frequently, is the forecasters are required to talk about categories of maximum wind speed, but then in their text discussions, they will say things like, there's an especially low pressure given the wind speed. And this was a large storm. And they've gotten better over time to explain this now, is that I think it's understood. Let me see here. It's understood that central pressure is an measure of intensity and size. And so be making that more quantitative in a bit. But yeah, so this has been a problem in the US for some time. As when we talk about intensity, obviously on the science side, there's the question is how strong the storm, but at the end of the day, the idea of communicating the risk is this issue. We have maximum wind speed, minimum pressure is very confusing for the public. So one particular case that was really bad, you may or may not have heard of, in 2012, Hurricane Sandy was one of the most damaging hurricanes ever recorded for the United States. It hit New York City and flooded the subways there. It was really bad for the northeastern US. And so there's a lot of data in here. This is the black lines, the time series of intensity in terms of maximum wind speed. And all I need to focus on is at this point is when it made landfall. And it was barely a category 1. It was arguably not tropical anymore. This is a big debate point. But it was a very weak storm in terms of its maximum wind speed. But for its minimum pressure, which is this curve here, at landfall, it had a very low pressure down towards 943 at landfall, which is typical for a category 3 or 4. And so Sandy was the biggest storm in the Atlantic ever. Again, it was kind of had hybrid tropical, extratropical characteristics. That's always a fuzzy line. But so this was like the most prominent case of a really big problem where this storm was really bad. But if you said, oh, it was barely a category 1. And if you say that to the public, they'll say, oh, well, I don't need to worry about it. And obviously, but if you look at the pressure, you'd say, ooh, I need to be worried. This is a big deal. And it was a big deal. So again, so as I said, people have come to appreciate this more, is that the minimum pressure integrates intensity and size. So going back to our simple schematic, so this is where thinking about the minimum pressure here in particular, or I guess this is the pressure deficit, I should say, the minimum pressure in general. And so bringing this up here first at just in the context of hazards and risk and impacts, is that it turns out, so it's work with Phil Klotzbach, and he had a paper preceding this that showed this as well, but I worked with him on an updated version in 2022, is that the minimum pressure is surprisingly a remarkably good predictor of total economic damage in the US. And so these are ranks. This is a rank correlation. So this is one simple way to show this. And so if you go down here, and this is the damage rank. So the most damaging storms are over here, and this is the minimum sea level pressure rank. So the lowest pressure is down here. So low pressures and high damage are down here. And so the point is that the lower the pressure, the more damage you have. And that relationship is, we do this as ranks because economic damage spans many orders of magnitude. Actually, we've more recently done this as a log linear regression, but I have that here, that's very new. But they're incredibly well correlated in rank correlation. So, and what's amazing is that does much better than if you use the maximum wind speed, which is what we currently use for our categories. And then our interest in this paper was to compare, is to say, well, and I'm not sure in the Western North Pacific if you guys, GMA, have thought, as a lot of people proposed, we should do some integrated measure of the wind field. And so in this case, we also tested that as we have data for radius of 64, 50, 34 knots in each quadrant. So we said, okay, let's do integrated kinetic energy. Let's square the wind speeds. You can calculate the areas of each wind speed and add that all up. And that also does worse. And so this minimum pressure is really just like shockingly good. Like I don't know why it's so good. Well, and we have thoughts, but like I'm still can't believe how well it works. This is something that doesn't account for exposure or anything. And if you go one step further, if you look specifically along the East Coast, sorry, I should have put some maps on here, along the East Coast of the United States, this relationship still holds up, but for when you go along the East Coast, Vmax becomes almost useless as a predictor. So whereas minimum pressure still does fine. So Sandy is a place on the East Coast, goes from Florida up to New York and Maine. So it includes cases like Sandy, where we often have these bigger storms, maybe starting to extratropical transition. They're just messier storms and bigger and weaker, and so but still may have relatively low pressures. And so it does better. Pressure does a lot better, and particularly the maximum wind speed is a terrible estimate, just like we saw for Sandy, of the potential impacts. So, so here's our scale. Oh yeah, question. Yeah.
How did they arrive at the IKEs? Are they using your wind profile model?
Oh no, so this one, sorry. So this is a reference just to the source of the idea. But all we do is we calculate. You have radii. No, this is not wind profile. So yeah, sorry. So this has nothing to do with my wind profile here right now. This is we have wind radii 64, 50, 34 knots in every quadrant for all the storms going back to 1988, and so you can use that to I forgot now. I think it's like a piecewise linear assumption that you basically calculate the area of a certain wind speed between each of those wind radii in each quadrant. So it's purely our best estimates of wind radii. Yeah, should clarify. So this is not my wind profile in this case. So, but the idea was, this should be better. It should be an integrated measure of the wind field, and somehow it's not. So, which I'll talk about. Question.
For this area, what is the percentage of damage due to wind or rain?
Oh, good question.
So
if I could tell you that, I would. We don't. That is often because it's often based on insured damages, and those numbers. Some of them come from private companies, and some of them come from so flooding is covered by the National Flood Insurance Program. Wind damage is usually privately covered by private companies. They don't like to share. And so that's always one of the issues with this data is we always just have aggregate numbers, but we don't have a breakdown. We can, the economic model I showed you, actually that's right. I didn't have the equation on here, did I? No. Oh yeah, so in this case, we actually get a regression that gives you coefficients for each of the terms. And so, but I don't have that here and I don't remember what they are, but you get contributions from each of these individually. And so in principle, that's actually a way it would change some area. Yeah, absolutely. Yeah. So on average, I can give you numbers, but like every storm is very different. So yeah, good question. Yeah, I wish I put that equation on here. So anyway, so I'm emphasizing, this is the thing we've been saying publicly for a few years is this, our category system, the Saffir-Simpson scale, if the purpose of it is to communicate risk, it is not doing that, or especially along the East Coast. It's not bad for the Gulf Coast, the more traditional storms. Oh, yeah. Let's see. I think we have all landfalls that are included in the best track database. So I don't think we did any. Phil did the actual data analysis. I don't think he did any exclusions for like whether it was.
The sounding case. Sandy gets Sandy undergo extratropical transition on 29
Yes.
October. So it's after the
So we definitely didn't exclude extratropical transition. So I'll just say the answer is no. Like we have all the landfalls, and that's actually part of the point is that we went along the East Coast. The farther north you go, the more storms are undergoing extratropical transition when they made landfall. So we don't want, if anything, I'll actually say this later, is like minimum pressure can allow us to maybe connect tropical, extratropical transition and extratropical cyclones in a unified way. So no, we're not excluding those. Yeah, Sandy is definitely in the data as well. So yeah, good question.
From the very strong asymmetric structure.
Yeah, and that's part of the, have a table of reasons why minimum pressure is nicer, is that the minimum pressure doesn't care how symmetric or asymmetric it is, whereas the wind speeds, like the Sandy's peak wind speed, I don't think it was in a place that made any sense, but that's how we define it. So that was how they tried to estimate intensity based on some random local, probably along a frontal boundary or something like that. So yeah, question.
Will you just explain why we see level pressure? Is that under one of the winds is that under? No, sorry, I said not the winds is that under 150 sea level pressure.
Yes. So this is the biggest storm on record. So storm minimum pressure, the bigger you can have the same maximum wind speed, but a bigger storm will have a lower central pressure because it's integrating over a larger radii. For the wind profile, and so I'll present a model for that explicitly next. So, so minimum pressure captures. So what I want to connect this to is minimum pressure implicitly has intensity and size, and now I showed before if you take a wind model and account for intensity and size, you can simulate the hazards quite well. And so this link here is that implicitly minimum pressure seems to be capturing the nature of the wind field and driving hazards and creating damage. So it's really trying to connect the physics here. And in particular, an important point. So I'll show this next. So like why does integrated kinetic energy not work? And first, I'll say this in a simple way: is like somehow the minimum pressure it's integrating the wind field, but in a specific way. And I'll show this next. But it's somehow must be capturing the right balance of intensity and size. It's not just because there's a million ways to decide how to integrate the wind field, and so somehow it's getting the balance right for how the wind field drives these hazards. And so in particular, I see that's why, there we go. Yeah, so this might be kind of a complicated plot, but what I'm trying to show you is, so what we did in the paper is looked at the weight, basically the weighting function that is used when you integrate something over radius. What is that something? And we tested, so when you do the red curve is the pressure deficit, where you're integrating v squared over r plus fv. This is from gradient wind balance. You integrate that over r. But other people have proposed integrated kinetic energy, which is r times v squared, because r is capturing the area as you go out, it's larger and larger area. And then people have also proposed the power dissipation, which is v cubed, basically. So it's like, do you want kinetic energy v squared, or do you want the sink of kinetic energy v cubed? And these both have an R in them. And so if you look at the structure of these things, the red is this one. So this is where the red is this one. So this is for a wind profile. We did this in a much simpler way. This is not the wind profile I talked about, but a very simple one. Actually, maybe it is my wind profile, I forgot. Anyways, this is a simpler wind profile. And then the integrated kinetic energy is this solid blue, and then the power dissipation is this dashed blue. And so what this is showing you is that the pressure deficit, it's very strongly dependent on intensity. So the winds near the R max are really important, but it's not the only thing. And this is, again, in wind pressure relationships, they work pretty well most of the time because it's heavily weighting the wind speeds near the radius of maximum wind. But also has a contribution as you go farther out from the west of the profile, but it drops off at a reasonable pace, a reasonable rate with radius. Versus integrated kinetic energy, especially, really strongly weights farther out. Like you're very strongly weighting, say, the radius of 34 knot winds instead of the winds near the radius of maximum wind. And then power dissipation is a little bit better because it cubes the wind, but you can see how it's where it's weighting the winds within the vortex. These are probably giving too much weight to the weaker winds that are still important, but they're not as, the strongest winds are still usually the most important. So this is an interesting exercise to think about, like, why might pressure work? And maybe there's some deeper physical reason why pressure, like some thermodynamic reason that minimum pressure or pressure deficit is really meaningful to produce hazards, but I mostly just think about it as like the way in which, what does it mean for the wind field? And how is it weighting the wind field at the end of the day? So that's trying to link the physics, something Icha-san and I were talking about, and I had this table from before, and so after discussion, I wanted to add it in here, mostly because I'd love to hear from you if you guys have thought about this. So I've advocated on physical grounds and that the minimum pressure is really nice compared to the maximum wind speed, but there's really other reasons too, and maybe some of you have encountered this. So obviously we, at least in the Atlantic, we do routinely estimate both of these, and that's something, I don't know if you guys do this as much, but because we have a lot of aircraft recon, so we typically get independent estimates of the maximum wind speed and from dropsondes to get the minimum pressure in the center. And so we have both of these, so we have a choice. And so again, as I've hopefully shown here, is the minimum pressure integrates the entire wind field, whereas the maximum wind speed is a single point. Are you doing 1 minute? Are you doing 10 minutes? Up to you to decide. Everybody does it differently. This is frustrating. This is on a single point. So actually, maybe I'll jump to this. Is it simple to estimate minimum pressure? Go to the center of the storm and drop a couple dropsondes, and you probably have a really good estimate. And that's all you need to do. Actually, this is old. There was a storm chaser, a crazy guy named Josh Morgerman, who maybe you've seen on YouTube, who just goes to landfall points and brings barometers. And if somebody wants to do that, we should. I'm like, great, send us the data so we have it. So it's versus the wind. There's lots of papers trying to say, well, okay, we flew through our plane this star pattern. What are the odds we missed the actual maximum wind speed? And now let's make an adjustment. Here's what we actually measured, but now we have to adjust it up by 5% because we may have missed the max wind speed because we're trying to find a single point somewhere in the storm. So, or even to Kanada-san's point before, of like when you get these big, odd, asymmetric storms, where do you even look? So that's very annoying. In general, on the physical side, is minimum pressure is really nice. It's formally, we've said it's an integrated measure of the wind field. It is also, that's from gradient wind balance. It is also from hydrostatic balance, an integrated measure of the mass, the temperature of the column overhead. So it is fundamentally an integrated quantity versus the maximum wind speed is very noisy. But if you've ever run high-res models, the higher resolution you get, the faster the point wind speeds are because you're resolving eddies and turbulence more. So it's not very well constrained. A nice thing for eyewall replacement cycles is the minimum pressure tends to hold steady. You don't have this issue of two concentric or of double wind maxima that you have to think about. On the climate model side, is that there's evidence from some colleagues or arguments that some of my climate modeling colleagues have said they really like minimum pressure better because it's just better represented in models. Often climate models, they're lower resolution, and usually that just means the storms end up being a little bit bigger and weaker than they would be otherwise. But those offset each other, and then the minimum pressures are actually better represented. Whereas max wind speeds, we know it's not going to do a great job sometimes with the maximum wind speeds, with the extremes. So, with that. The maximum speeds. Oh yeah. So anyway, so this is, and then these are the other things we just talked about. So I need to go through these again. So anyways, these are the more practical meteorological arguments for minimum pressure. So I'm just sharing this all because this is something we've been saying, me and Phil and our colleagues. We've talked to the National Hurricane Center about this. We've talked to Chris Lancy. He agrees. It seems like the forecasters now really understand this, and they talk about it. They talk about minimum pressure as much as they can in their discussions, but I'm not in charge of trying to change how we categorize storms. But in my opinion, if the storm categories are meant to convey risk, then let's see here. Then if they're meant to convey risk, then minimum pressure might be better. So
trying to keep that to the general public, because people can better understand things.
Yeah, and that's like one counterpoint is that there's more intuitive understanding of wind, but I mean, I don't think there's no drawbacks. I think there's, and I understand the hurricane center, they have to deal with, they have lots of stakeholders and lots of people who have different interests and there's literally financial interest, insurance markets move on what the hurricane center says. So I'm not blaming them. They have a very complicated job. So, but it's just, I think, tough when it seems like, for a lot of reasons, this is a really much nicer quantity to work with. And we're saying integrated kinetic energy is probably still better than Vmax, but that's actually another point, is that you could put on here, why not do integrated kinetic energy? Well, now you need intensity and size in every single quadrant and you need way more information. So you could do that too. And I think hopefully we've shown that it's definitely not better than the minimum pressure. But you could do that too. It's just like, this is one measurement. And from one measurement, you get so much. So
So could you go back one slide?
Sure, yeah.
So related to Margaret's question, I think it means, we need to put more weight than, the square, right? So it means the minimum flow pressure, they give more weight to the center, inner core region.
Yeah. I mean, it actually peaks at
but not as much as the Vmax. Vmax is
exactly. Yeah, if you put Vmax, it'd just be like a lot higher.
So
exactly.
I remember one paper published by Ishijima-san. You met in Kyoto. He is a wind engineering professor, but his paper saying that wind-related damage is related to the force.
I see.
To the force of wind speed.
Yeah.
So I think of course different kinds of hazard gives a different function, but I think the square maximum wind speed is not enough.
Yeah.
Might be so you can if you want to decompose every hazards, maybe you can clarify what is inside.
Yeah, I guess there's one distinction between, you're saying if you take the maximum wind speed to some power, what should that power be? And yes, it's at least 3.
Right.
There's people who have done, if you do total economic damage numbers, it's like 6. It's huge. But so that's different. That's a little bit different than this. So this is saying, how do you weight the wind field?
Right.
But if you just do the Vmax, yes, there's also arguments that it shouldn't even be Vmax alone. And so that's
just I remember, the second order in to a square, then cube, and fold, and I just remember, Nishizuma-san showed.
Great. Yeah, question.
You showed there is a county level data of damage.
Yes.
So if we plot the damage is as a function of R over R max, then we can discuss which slope is better.
Sure. I just realized that I misspoke. We don't have county level damage. What she did, we have only aggregate damage, and what she did was to model the county level impacts, and then add everything up and compare it with the number. And this goes back to Nino-san's question. It's like, we don't know, we don't get the only numbers we're ever given publicly is like the big total number. So we actually, I wish we could do what you said. If we had actual county level damage, that would be amazing, because then we could really model the county. We could actually do exactly what you said, but we can't do that.
Alternative option, yeah, you can draw the model damage
Yes.
as a function of R over R max.
Yeah, exactly. Yeah, so we could, so in principle, the maps I showed of the aggregated damage, but yeah, that's the sum of a whole bunch of individual storm damage distributions. So
And you can find which why the pressure is so nice.
yeah, that's true. That's true. You could probably bridge that gap. That's a good point, actually. You're right. Is maybe the damage also drops off like this from. That's what you're saying. Is that, yeah, that's a great question. That's a good idea. Yeah, I'll ask my colleague about that. That's a great idea. Yeah. Yeah. Question.
A typical running profile, that every term like diverges. So do you apply some function?
What do you mean FE diverges?
When you integrate.
Yeah. But you just integrate this dr. So this is just as the wind speed goes to 0.
Yeah, but d is lower than r to the -1. So
yeah, but it's not an integral of r dr. It's actually just an integral of dr, because it's great in grading wind balance. It's dp dr equals this. So it's not r. It's purely the integral of this. These ones have an r because this is an area weighting. It's actually integral. It's r dr for these, but this is just dp dr equals this. So, or one over rho is density also.
yeah, but still, if you put d equals to v0 over r or something and integrate over the radius, then it diverges.
I mean, so sure, but that's the point. So going back to my wind profile model, there's a finite edge to it.
Oh, okay.
Yeah, that's maybe one of the simple ways where, yes, if you allow if you propose a wind profile to go forever, you violate Kelvin circulation theory. You basically have negative vorticity to infinity, which means you're that's not allowed. So that's one place where yes, you have to. The storm actually has to go to 0 at some point at a finite radius. So in this case, I think actually we just integrated in from R34 because that's all we had.
Oh.
And I think I'll show this later. The pressure drop outside of R34 is usually only a few millibars. It's not super strong. So if you let the winds go to infinity, then it'll blow up. But that's a very good reason why you cannot go to infinity. It really has to stop. So
Yeah. I just wanted to.
No, it's good. Yep. Yeah.
I'm curious about how do you define the damage related to
that's not my job. I mean, mostly through insurance. Like my understanding, I think it's still true, is these numbers, the insurance companies report insured damage based on claims. And then I believe the standard, and I don't know if this is still true, but for a long time, the standard is to double that number. So insured claims across all damages that or all hazards come to $1 billion, then they'll double it and say, well, the total damage was probably $2 billion. And don't ask me why that's where that comes from. So that's for the economists. You can ask. Yeah. So it's very crude. All these numbers are very crude, and this is where the only benefit is that they span many orders of magnitude. So you could argue that it's not a big deal exactly if it's times 2 or times 2.5 or times 1.5, because you're comparing. We do rank correlations because you're comparing something that costs $60 billion to something that costs $60 million. So it's there's a lot of room for variability with it, and it won't be very sensitive. So yeah. Well, I'm glad I added this morning, so I'm glad I put this in. So, oh yeah, and I'll just last point, which I brought up before, getting this on is, I'm just putting this out there. I just like the idea. We use minimum pressure. I should have picked up this from his previous talk. European windstorms, extratropical cyclones. You guys experience those a lot, obviously, here in Japan. Minimum pressure is what we use for those. Nobody tries to estimate the maximum wind speed in an extratropical cyclone. And so I just like the idea of minimum pressure as a way to unify across tropical transition and extratropical status. And I'm not saying there may be still trade-offs in doing that as well, but yeah, like here is, it would be really bizarre if anyone said, I want to tell me what category it is the extratropical cyclone is, the blizzard that we're going to get. What's the maximum wind speed? I don't know why we would do that. So anyways, that's the end of my my bit about minimum pressure in general. So yeah, if you guys have thoughts, I'd love to talk about it more. So okay, just getting back to I don't know why I put this in here. I guess I just haven't said it yet. Is the response of minimum pressure to warming. I talked about the response of the wind field to warming before, and you just extend this to the pressure deficit. Is that if the storms become a little more intense, then oh yeah, that's right. This is why I put this in here. Is that if the storms become a little more intense, they don't change size. That still means the pressure will become lower. And so just based on all this, it would suggest that storms ought to become possibly more damaging. So, so this is really trying to connect now all the physical principles of everything we talked about yesterday, in terms of structure, size, and then the expectation that storms will get a little more intense. And so we expect the pressure to drop, and so that's what make them more damaging. So, oh yeah, oops, lower pressures. So yeah, and I guess I should say lots of studies have also shown the pressures drop along with the increased maximum wind speeds of warming. So yeah, so it's just this section. I just wanted to connect this because I think it's a really nice way to think about the applications to hazards and impacts. I think it's helpful to think about, again, the idea of projecting into the future where we don't have data, but we have lots of models, and trying to really synthesize the things that we see in models in a simple way as possible. So, so yeah, that's this section. I guess I'll pause there if anyone has any other questions on this. Okay. So,
if you want, you can take a break.
do you guys like to take a break, or we?
So
I'm fine with going another one and then take a break. It's up to you guys as well. If you guys, start strong in the morning, I guess.
okay, so maybe
Short break. All right. Why don't we do?
okay, 15 minutes break. We will resume 10:35. 10:35. Yes. And
Yeah.
photo.
Good idea. Good idea.
Thank you. So just we take photos, so how we do take photo. So ここで撮ります。どこがいいですか？はい。ここで撮りましょう。
アウトサイドがインサイド。
ですよね。あとがいいですね。いいですか？少しちょっと出ますけど。So, yeah, we can go outside and take photo. Is it okay?
Yeah, of course. Yeah, no, perfect. Let's do it another time.
Yeah.
Great idea.
So, such a sunny day.
Yeah, it's beautiful. I think we should do the seminar outside.
Photo.
All right.
委員会の、これの委員会のマーク。
There's always, that's it. It's good to visit. And
But I know, but I.
So I know a little, I've learned like for some reason, I never like learned about it. It's just like a stationary product. They're not serious, they're not actually the ball, like the next Oh yeah. I was gonna, that's what I wanted to ask you, like, whether you guys. Yeah. Earlier in the one hypothesis. That's so I think that's where we've been pushing really hard on the last year now. Seeing the environment. Maybe we're never and so maybe show you. Steve's done really, he's really on it. He's done the whole extra trouble. And I was breaking it down. There's just one of the tracks are the most. And it really
Exactly.
Basically saying, like, what's the, you know, is there a certain type model of types of tracks that are all you that? All you need to do is track a cycle. How often are you that type of track? That's not a model. The model tornado breaker is going to have a sensitive tornado. Yeah. You're right now, you're not doing tornadoes. Yeah. Sorry. We did jump it down. Yeah.
Make sure to fire out. They're not.
Okay, so you want to do that for me?
Okay, I'd rather do that.
That's great too. We should use. We have a few also, we should start in.
I mean, the other month.
And one of them. Suggestion.
Yeah. That's the one.
So, that's your. Most of the thing is you're the only people that always have to go out. Which is really cool. So, yeah, are you around after, or do you have to go? But in the shaking of
That's why ignorance is bliss. That's just
Okay, maybe you can, yeah, I guess that's something you have your own time. I have seen. What's your, yeah, how many people are, let me get you. Barely trying to stay awake, submitting an abstract, and then I was sitting there thinking like, you're gonna totally extend it.
I do want to make sure that everything's fine and it's fine. I'll see this in here.
ちょっと参加が見えるので、ぜひ参加してほしい。あですよね。あ、そうなんです。いや。参加の趣味の参加なんか。そうなんです。一人だけだ。
And also, I was actually trying to print. Wanted to do this part. So it's simple. So but it's hard. I haven't for a while, but I haven't. I was trying to sell it this I can do this quick. It'll be. You have a good night sleep last night? I slept like a baby.
Oh,
Oh yeah, Ernie says hi.
then let me show you the paper. By Nishijima-san.
Oh, perfect, yeah.
He showed his so his paper is saying as this is the wind speed and the probability of damage of housing. He is working on a wind engineering.
Oh, great.
Their parameter is to the force of the wind speed.
Is this damage
Yeah.
at like what scale? Is it like house scale or okay? And then the wind speeds are estimated.
It's kind of probability of damage.
Well, okay, send this paper to me. Then I can. Yeah, I'd love to be able to cite this and show
That's
this.
the wind side, but I think you can find similar kind of stuff for coastal
Yeah.
rainfall hazards.
Sometimes just be surprised how much. If this is not Japanese data though.
Yeah.
Okay, that's what's nice. I like getting out of having independent
Right.
view of this from other countries. Right. But yeah, it's done. You can send me that, or we can afterwards we should share. So
It explains why the minimum to low pressure explains the better damage.
Ernie AG says hello. Or Ernie AG, I sent him the picture. And he says hello. He says send you his highest regards. So yeah, very nice things to say about you. Should I get started now?
Again.
Okay.
Okay, so we'll come back. We do our section 4, right?
Yep.
Okay.
Moving on to section 4. So, all right. Thanks everyone. Yeah. So next, I'm going to talk about some simpler predictive models. And again, maybe everything I've shown has already been too simple, but I actually want to make them more useful. So maybe that's another way, instead of saying simple, is useful models. So how can we create something that's more directly useful? So I'm going to talk about models to predict the minimum pressure, models to predict the radius of maximum wind, and then actually a new analytic wind model that I really like. It's brand new. That can replace my other model that I've sold you on being so great, because it's actually not that easy to use. So a key thing I mentioned at the very beginning yesterday is this is the place where I'm really interested in getting beyond physics. So I presented to you this case of all this physics. The physics is very rigid, in part because we have to make assumptions. Simplifying assumptions, and that may mean that you can't actually capture the real world correctly. So my wind model, for example, I think it's really great, but it has assumptions in it, and maybe it could be something a little bit different that's similar, but something a little bit of a deviation to allow you to better capture the real structure of storms. So hopefully you'll see what that means. So the first one is a model for the minimum pressure. This is work with John Naff and Phil Klotzbach. So we're back to our simple view here. The minimum pressure, the pressure deficit. I don't know why I put P in. Should have put delta P. So this is a paper that just came out earlier this year. And so really the goal is, set pressure is the integral of the wind field. It's the integral of the wind field. Well, nobody wants to take my wind field model, which requires 1,000 lines of code, and then integrate that to get a minimum pressure. So can we do something faster than that? So an easy to use equation to predict Pmin, and particularly from routinely estimated data. And so for us, that's going to be, again, the radius of 34 knots. So now that I understand you guys have different radii, you can do everything I'm doing here again, but with the radius of 30 knots, for example, you'd have to retrain things based on the data for that, or make some sort of an adjustment. Okay, so the minimum pressure is really, at the end of the day, it's really the pressure deficit, which is the difference between an environmental pressure outside the storm and the central pressure. So that's really, the pressure deficit is the part that's the integral of the wind field. So I think I've said this enough times now, but okay, yeah. So again, you can get the pressure deficit by integrating the wind field using gradient wind balance. And so here I'm showing you been having slightly different versions of wind profiles. In this case, I'm doing something that again is breaking from my wind model, which is that it turns out we showed this, and this is sort of this wasn't the main focus of all of our paper in 2022, but is as part of actually that the weighting functions I showed before, is I wanted to do something simpler, and so I used a modified Rankine vortex, and in there we mapped on, this is a R over R max versus V over V max, so R max V max is here, and then this black line is a modified Rankine vortex with an exponent of minus 0.55. So in this space, this is just a minus 0.55 exponent decay in this space. And then I mapped onto that all the data for our best track database for a radius of 34 knots in blue, 50 in purple, and 64 in red, 64 knots in red within this space. And then the medians curves are in here. And so especially I like to emphasize the blue. Then you'll see that this data does a pretty good job of lining up with this modified Rankine structure. So, and so that was convenient. And I'm going to use that here because what it does is it actually allows, if I use a modified Rankine in here, and then here I use an eye profile with parabolic, doesn't actually matter very much the shape of this for the central pressure deficit. But if I take this very simple, so parabola and then modified Rankine, here's the equation, modified Rankine, I can actually plug this in and derive an analytic prediction for the central pressure deficit. So what does that look like? Is you get this equation. I'm going to step through this equation here. So this is really nice. And so actually I go one step further and make more approximations, which is minus 0.55 for the exponent is close to minus 0.5, which is square root, which is easier analytically. It makes the math a lot simpler. I assume a constant density, and then I'm ignoring anything complicated about the boundary here, as we've talked about before. So keeping things simple, you get this equation. And so what is this showing? And there's a bunch of algebra that reduces to a much simpler, this final form. And so you get here, this is just a constant, the wind speed at some outer edge. So these R naught and V naught are the radius you start at integrating in. So you could imagine 34 knots if you want. So the maximum wind speed here, as you go to the square, here's the square of the maximum wind speed comes in. So negative sign means higher maximum wind speed, lower. The pressure deficit is defined as negative. You end up with the Coriolis parameter times the size, the outer size. Again, think 34 knots if you want here. And that parameter, they come together. This is actually something kind of weirdly fundamental, because they're not separate, they're together, the product. And then there's a third term, which is the ratio of these two things, well, I guess the ratio of this to just Vmax that pops up in here. And this is a small modification. It's not totally negligible, but it's small. So again, now giving you an equation that actually literally shows you it's not Vmax, it's Vmax squared. And then it's size times the Coriolis parameter. And then there's a modification term. So this is where, up till now you might say, I like theory so much, why wouldn't I just use this equation? It sounds really nice and mathematical, but I made all these approximations. And so the point is, the physics has given us something where it's identified parameters, in particular combined latitude in the Coriolis and size into one single parameter. But theory has biases, it's hard to calculate. I make all these approximations. And so I don't want to worry about those things. So in contrast, we have data, which is at the end of the day what we actually want to predict. And so I'll call it unbiased truth, and the best estimate of the truth. But then the relationships among the parameters are unconstrained. So you have all this data, but how would you put it together? So physics actually tells us how things ought to be put together. But then the observations are the things that we actually want to be able to reproduce. So the idea is to try to get the best of both worlds, is to use the physics to create just an empirical model that uses the physics to define the predictors themselves, and then use the data, though, to estimate the actual relationships. So that I'm not completely constrained by the specific structure of whatever wind profile model I use, whatever physical assumptions that I'm making. And this is even where, going back, you asked about the boundary layer, this is the part where instead of saying, well, in theory, I should go to the top of the boundary layer, integrate in, and then go back to the surface. It's like, well, this would just let me say, why don't I just start with the surface and go to the final answer? And maybe the empirical model can build in whatever impact going up to the boundary layer has, like whatever impacts the assumptions that you're making are on the actual relationships. So what does that look like? So I'm taking the same form of the equation that I got from the physical model, the pure physical derivation, where I have these three predictors here. But now instead, I'm just gonna do a simple regression model. Where I'm going to try to estimate each of these parameters. And this is just a pure linear regression here for the central pressure deficit. So this is where the data is going to give us the actual relationships. So the theory has numbers for these, and they're not unreasonable, but maybe the theory says this should be 10, but the data shows it's 12 for whatever reason. Let's just follow the data. That would be nice. So we're as unbiased as possible. So what we're going to do for this is take data from our best track database from 2004 to 2022. What we're actually going to do is center this specifically so we don't just use the best track data itself, but we really need independent direct measurements of the minimum pressure. We want to make sure we're getting as good an estimate of the minimum pressure as possible. So what we do is actually start from where we have aircraft estimates of the minimum pressure itself, and then we interpolate the other variables to those times if they need to be interpolated, or this is the center point of the data. We also estimate the environmental pressure from this is from NCEP's climate forecast system and the GFS analyses. John led that. It's a simple estimate of, I think, the azimuthal mean flow getting to some reasonably low wind speed. So so then otherwise, if needed, we interpolate these all the other variables to the time where we have the minimum pressure estimate. And so the other part is we're going to do some filters here. So this is the map of the data that I'm showing in the end. So this is the actual minimum pressure, just scatter plots. So we're using the western kind of southwestern Atlantic. So we don't want to go north of 30. We're trying to avoid extratropical transition here, at least for that initially. We want to be reasonably far from the coast. So what we do is say the distance to the coast has to be greater than the mean 34 knot radius, so that hopefully none of our 34 knot radius estimates are believable. They're not impacted by land. Just a very basic low intensity threshold. And then we need to have 3 or 4 quadrants of data for our 34. So we just can match up all of that data, and we're going to bin things into fixed increments of each of these quantities, the Vmax, F, and R34. Okay, so what do you get when you do this? Let's see here. Oh yeah, there we go. Okay, so I'm just going to show you the answer, which is, so you now have numbers in front of these, a couple of technical points. So for Vmax, we do a really simple estimation. Technically, from the theory, it should be the azimuthal mean maximum wind speed. And so what we do is do something very simple that we've done for about 15 years, which is to subtract a little bit over half the translation speed. So we know translation speed will enhance the maximum wind speed. So it's just an extremely basic estimate of how to get to the axisymmetric maximum wind speed. So we have this equation. So we walk through. So lower pressure, so larger pressure deficit if you have stronger winds. If you have, so the important point, signs matter here now. So minus means higher value of this, lower pressure. So negative here, we have a negative here. So larger or higher latitude storms. And then this one is a positive. It's kind of a weird term. I spent a lot of time, know that I have a great explanation of what it means. But anyways, it's a term, again, it's a small but not totally negligible modification that this amplifies this term and reduces this term. So so we get an answer, and it gives numbers that seem pretty reasonable. So or at least qualitatively reasonable. So what does that look like now if we actually compare the model prediction to the data? And so this is just all the data put together. So on the x-axis here is the observed, so I should have put delta P here. These are observed pressure deficits. And then this is the model predicted pressure deficit. So the black line here is the 1-to-1 line, the perfect prediction. And then what I've done is just put all the data on here. So all the black marks are data. And then what I try to do is to show, we want to see is whether there's any conditional bias. Was it better at high versus low pressure deficits? And in particular, there's a lot of data up here, less data as you events. You want to be able to see the full intensity distribution. So, and so you can see, this shows you the spread. Let's see, this is conditional median. I think this is interquartile range and 5 to 95th percentile range. But so the median follows pretty closely along the 1-to-1 line. And even as you get down here to these outliers, this is Hurricane Patricia down here, which was the most intense. I think it's still the most intense you've ever observed. I forgot now if you've passed Patricia. But it's even doing a pretty good job with these really, really, really intense storms. So Patricia was out here in the, actually, I guess this must be Patricia right there. So, yeah, so it explains, let's see here. So, yeah.
I have a comment.
Yes.
Go back once.
Oh, yeah, definitely.
So, you developed a model to estimate minimum zero pressure from maximum wind speed.
Yeah.
But did you try to develop a model to estimate the maximum wind speed from maximum wind speed from minimum zero pressure?
No, but you could just install this equation for Vmax.
Right.
So, yeah.
The reason why I'm asking is,
Yeah.
yes, of course, minimum sea level pressure is more easy to observe.
Yeah, no, you're absolutely right. So I think that's the idea is you could, what I like about this equation, when you have a nice simple equation, that's one equation.
Right.
Yeah, you could do the reverse. If you have this information, you can solve for this. Even actually I've had discussions of people, in the past, we might have had maximum wind speed and minimum pressure. Could we infer size from that? And so I think that's, equally doable. So yeah,
Right.
so I haven't done that, but it's as easy as just solving this equation.
Yeah.
So yeah, great question. Okay, so this is nice. So this explains 94.2% of the variance. It's really good. RMS error of 5 hectopascals. So in general, I think it does a really good job. What's cool is so you can then take these models, and this is something I really like to do, is simple models that are empirical models, is you can do experiments with them. You could try doing models where you don't include certain terms. And so what you can do is, for example, so if you have only Vmax squared, you get 86%. So, and I think this does worse. I forgot if I have this on here. I think Vmax alone is actually a little bit better than Vmax squared alone, which is interesting. But so the point is that wind speed alone gets a pretty, wind pressure relationships are pretty good. Like there's a reason for that. You're getting a lot of the variance because most storms are generally a similar size. It's really the outlier size is really the big deal. But then if you add in Vmax squared and this Coriolis times size term, you get up to close to 93%. And then if you go to the final model, I think I had it switched, just 94, and you get another 1.5% of variance explained. So this is where that third adjustment term matters. It's not a huge jump, but it's still, you're still doing better with it. So, which is also just fascinating. And this is where you're really testing the physics of, again, we use the physics to define the parameters. And so it actually lets you see how each of those contributes to predicting the minimum pressure. Okay, I see. So I just set that the opposite direction. And then the other thing that's cool, and I guess I didn't put the actual explained variance, is you could also imagine, why not just be empirical and just give it each of these parameters on their own. And I don't know I forgot what it was. Maybe you get 92% or something. If you just threw these in, you don't do as well as this, which maybe is surprising, but I think that's another place where now the physics has added value. Because it's told you how when you do empirical models, you have to decide what your predictors are. And so the physics gives you guidance on that. And we're actually have empirical confirmation that this specific combination of parameters is the best, which is very cool. So, yeah.
Quick question about set up the linear emission equation.
Go say it again.
Yeah, the setup of the linear
Oh, yes, yeah.
equation. So I understood P mean is coming from the equation.
Yeah.
How about Vmax and the radius of certain.
Yeah, so these are both from best track data. And then they'll be interpolated to the time and the minimum pressure observations. And so the idea here is whether you're thinking best track or operational. For us, this is estimated every 6 hours by the National Hurricane Center, this, and then we know what latitude we're at, the center of the storm is. So these are things that you should have, going back to your question yesterday, these are things, at least for us, we would have, any forecaster would have on their desk every 6 hours. And you could even have forecasts. We have forecasts for this, and forecasts for this, and forecasts for the track. And so you could forecast the minimum pressure based on this as well.
But since you have an aircraft observation for pressure, we're 20 feet.
Yeah.
That means Vmax and radius of north is also most likely based on the aircraft observation.
Yes, so that's the thing, is this is where, like, for minimum pressure, the one downside, I think, to minimum pressure is that we have no way to remotely sense that. Like Dvorak is, I mean, I guess you could train Dvorak on PNID, but it's normally trained to Vmax. We don't have this. You need, if you don't drop a drop sonde in, then you really don't have any real estimate of the minimum pressure. So, but yeah, so these are direct aircraft estimates. These estimates, are whatever the Hurricane Center has decided based on all of the information. It could be from SAR. Like, this is the part where every observation for Vmax depends on whatever data was available for that time. So maybe you had a SAR overpass and they had really good data, or maybe you flew a plane in and took data. So there's more than just aircraft that can go into estimating these other parameters.
But for the training data set, the time of the data sets only into the time when you have an aircraft.
Yeah, exactly. Yes. Yeah. This is not the entire data. It's just here we start from this and then we interpolate everything else to those times. So that's our data set. Yep. Yeah.
Can you compare with the theoretical relation?
Oh yeah. Yeah. So sorry. This one. No, you wanted this one. Yeah. So I think the numbers. I remember. So this is 5/4. This is. This would be 4. I think this is quite a bit bigger. Let's see here. 4 times. I have this in the paper. We're doing it. 4 times 17. So this would be like 50 or something, or 60. And then this is maybe like 200. That's 17 squared. So, and then I think, so they're different. They're not, let's see here, what did we get? So 5. So yeah, this is quite a bit smaller. And then this is somewhat smaller. So,
so you can go. Yeah, there is a V0 and V row. So,
yes, and then there's row. Oh yeah, right. Row, which usually that's 1, but it might be. Yeah.
So yeah, you can. So can we compare estimate V0, right?
Yeah. You can.
From the coefficient derived from data observation.
Well, so V0 is what you pick. Like this would be 34 knots for how we did it. So this is
34.
Yeah. So this is, you have to do it in meters per second. So this will be 17.5 meters per second squared. So yeah. So they're different. So they're different. So they're quantitatively different. They're not. It's like this is the coefficients you get are quite different from. Let's say they're like this right sign and like probably the right order of magnitude, but they might be a factor of 3 or 4 different from each other. So yeah. Yeah.
I think there's a Dvorak analysis.
Yeah.
There's a table results from Vmax pressure.
Okay.
And how your plots compared to.
Great question. I don't know. I never looked at that. I actually am curious because I've never done Dvorak analyses or anything myself, so I don't know. My understanding is Dvorak, I don't know what the basis is for the conversion, because my understanding is Dvorak is just the structure of the cloud tops of the eye, and in my view, the things where pressure diverges from Vmax is if it's bigger or smaller. And latitude too, I guess, matters, but like if it's bigger or smaller, the structure could look exactly the same. It's just a different scale. But I don't think Dvorak would account for that, so I don't really know. I'm assuming that's just an empirical link from Vmax to Pmin, but I don't know. Okay, yeah. So it's probably some, follows a wind pressure relationship is what I would assume. I don't know if you know anymore.
No, just I agree that in our town, especially, it represents our term which we cannot from the world activity.
I think usually the Prof technique, as you mentioned, the Prof technique focusing on the inner core structure. So it can correspond to the V max squared term, but it cannot correspond to the second size Coriolis multiplied term. So just I think of course initially you can first as a first order squared maximum speed should be related to the pressure deficit, but size and Coriolis parameter also impact on the Williams pressure. So second term can account for that. Yeah. So I just agree with this explanation.
This technique may be better than the graph with the second one.
Yes. So
I think what I'd say is it's always like a big thing we talked about, like why we started from the aircraft jobs for PMIN is like this doesn't work if you take all the data, like best track data, most data outside of like I don't know how much in the Western North Pacific there's most data is you need independent estimates of Vmax and PMIN. Otherwise, if in the best track database there's Vmax and PMIN there, but 90% of the time it's somebody who just applied a wind pressure relationship because they did Dvorak and then they said Dvorak says 130 knots, and then I look up the table and here's where PMIN. That's not independent, and so you don't want to create a model. The model is going to dramatically underestimate those relationships. Then if like the data has specific relationships already built in that are not physical. So yeah, it's important to get independent estimates. Otherwise. But yeah, so at the end of the day, if you only have one, if you have one estimate of one, then you could use this to estimate the other.
So several years ago, Aizawa-san and I developed a model to estimate minimum absolute pressure by a linear regression. But at the time, this Vmax squared term is replaced by Ci, our number, and also we also contain, but nevertheless, we also contain the H bar count in our model. So because it gives better results. So.
You've already done.
Yeah, you've already done. I should put your face up here. So yeah, so maybe that's where you just his model could maybe skip that step if you don't have if you have no data at all for these, you just have the Dvorak, and I think that's an awesome way to do it. So yeah. Okay, so here. Just a couple other tests. So we trained it on excluding things close to land, but if you apply it to those cases, it still does a pretty good job. You get 93% of the variance explained. So this is the map showing now. So this is truly out of sample, and even like arguably you have to be careful a little bit because you're close to land, but it still does a pretty good job. And then even at higher latitudes too, which is a much smaller sample size, but and so you do much worse, unsurprisingly, but you still get 88% of the variance. It does pretty well. There's a little bit of a low bias as you go to these higher intensity ones. I think I have, yeah. So this is one place where minimum pressure may be somewhat problematic. I'm not quite sure, but you're dealing with extratropical interactions now. So this is, we're applying, whether it's the theory that breaks down or whether it's a theory that breaks down or just now your wind field is much more asymmetric. And, we also probably, if you're close here, you may not have good wind quadrant or radii quadrants to the west. But so again, it's just showing you how it's still doing a pretty good job even as you go to higher latitude. So, but maybe there's something here where when you get to really low pressures, now the model is predicting a much lower pressure deficit than it should be. So I don't really know why. I think that's just something to think about. So maybe it makes it harder. The idea of the transitioning, unifying from tropical to extratropical. I don't know if maybe there's actually some issues with that because of the asymmetry. So, and then just showing some examples of cases with different intensity and size evolutions. So I gave some descriptions of what these are. This is just a really intense tropical cyclone, Patricia. Ike had quite variable intensity, size and intensity evolutions. Rita was something that expanded and had rapid intensification periods. And then Michael expanded. Michael is a little bit like Helene. It expanded as it moved north through the Gulf of Mexico. Whereas its intensity stayed relatively constant because I didn't include those in here. But so yeah, just the solid line for each of these is the model and the observations are dashed. So in general, it does a pretty good job. Actually, I put on here, don't have the figures to show this, but often the places where there's some more deviation here is this is often Ike was interacting with in the Caribbean and Cuba. I don't know if that explains it, but there's just reasons why maybe there were some issues. But overall, it does a pretty good job. So just some examples there. For Sandy, it does less well. I think Sandy, which you know, I realize, these down here are Hurricane Sandy. So again, that's where it predicts a much lower pressure than Sandy actually showed, but it still predicts that it has a low pressure. So, okay. So then the next step is to go one step further. So I said the motivation is to make this as easy as possible using operationally available data. So there's the one thing we've talked about, the pressure deficit, which is I just went through. But this side, we were actually estimating this pressure from GFS analyses. So that is a thing that could be doable in practice, but it's not done currently operationally. But the one thing that is done, I don't know, do you guys estimate the radius of outermost closed isobar?
I think people are looking, but
okay.
not published.
It's not my favorite radius, but it is estimated. So we have it in the best track database, the pressure and the radius of the outermost closed isobar on a map, and then the pressure of that contour.
Subject.
It's I think, I mean, to some degree, I think it's more an issue that so like if you take a vortex and you put it in and it's sitting by itself, it'll have some outermost closed isobar. If you put it in a field that has a pressure gradient, the closed isobar, the outermost closed isobar will become smaller. Like you will open up an isobar. So there's some subjectivity, I think, but there's also just like some physical reasons. It's a little weird, and it's a storm embedded in a flow that's moving faster. You probably will have your outermost closed isobar won't be as far out. So there's just some weird things about it, but it's in the data. And so what we tried, and this is something John Knapp had done also in past work, is just to say, well, we have this. That's outermost closed isobar is probably like pretty close to the actual true outer edge of the storm. So if you just take this and you add 2, actually we can test this. So this is the best outcome, is to add 2 hectopascals to this outermost closed isobar and use that as the environmental pressure. And how well does that work? And so this is a fully, now you're using only variables that you have operationally. And at least for us, we have operationally, I should say. And so this is how the model looks when you do this. And this is, now what we're doing is just taking, this is no longer the aircraft-centered database. We're just taking the best track data. So, so just all available regular operational data. So this is the map of what that looks like. And so taking the same model and applying it for that whole database. And so you get what looks pretty good, some pretty consistent skill all the way down to low pressure. So yeah, so it seems to work really well here. This is the best fit. Again, if you change this, you'll shift the data up and down. So this is the best fit to make it unbiased across intensities or across minimum pressures. So anyway, so this is the model in 3 steps, which I've sort of shown before. Here's the bulk of the model, and then you need an environmental pressure. And then when you have the environmental pressure, you just add them to, again, this is defined as negative. So the environmental pressure plus a negative gives you the pressure. So yeah, so that is our minimum pressure model. Trying to skip over all the complicated things. Again, the physics, all the physical assumptions that are built in, it's nice to not have to worry about that if we can. So any questions on that? We're going to take a very similar spirit to the radius of maximum as well. Yeah, so this goes back, this is from a couple years ago now, with me and John, working on this. And again, so I switched the order of this, but really we did this first with Rmax and then did it with P-min. So now we're interested in the radius of maximum wind. So it said, you know, I've convinced you we have this model that can predict the radius of maximum wind, and that's nice. But maybe we want to get away from the physics. So just a quick note. So yeah, Rmax, again, you know, you could argue actually at the end of the day that getting our max right is the most important. So our max sets the footprint of the worst hazards if you want to really be able to predict exactly where the really strong winds are going to be. And usually the strongest storm surge is in the vicinity of our max on the right side. So again, we'd like to predict our max. And so can we do that? So this is where, again, here I've shown you my model. I think it gives a nice first order prediction of our max from, say, our 34 knots, but it's idealized, it's rigid. And actually Dan Tao and her collaborators in 2023 showed that there's really an issue is that my model is it's really, I guess, the complete model, but in particular, the inner model that I said I don't want to have to think about. It's very rigid. It makes a very specific fixed relationship in angular momentum between our max and our 34. And what Dan showed was that real storms, that's not true. Like there needs to be another degree of freedom, of variability in the inner core here. And so so what we'd like to do then is can we marry physics and observations? So let's try that out. So just one other note, motivating this is one idea is, so you talked about maybe you have estimates of Rmax, but maybe you don't. R34 tends to be more smooth in time and space. It helps that it's out in the non-convecting or the less convective region. It's less turbulent, whereas Rmax is very highly turbulent. And especially this is where when you're working with models, it can be very sensitive to horizontal resolution in models. So maybe you don't want to deal with that. This is just one place where Rmax is a little bit difficult. So whereas this outer circulation is much less sensitive to these issues. So maybe estimating this and then going to Rmax would be nice. So it depends on the context which you're working on. So so what we're really trying to codify is what's been known for a long time for how Rmax is varies. So we know that Rmax is smaller for larger Vmax, for smaller size and lower latitude. I showed you that before. I don't think I need to go through this again. We've talked about how Rmax tends to vary. So so this is where, in general, Vmax, this is again, we have three things that can change Rmax. So Vmax, outer size, and latitude can all be changing. So I guess maybe in this case, the storm is moving north, its latitude is changing. Maybe its size is changing some. Vmax is changing. This is Hurricane Michael, it's intensifying over time. So all these different factors are changing. So how do we think about that for Rmax? So obviously there's other people have developed empirical Rmax models before. So again, at the end of the day, we want an easy to use equation to predict Rmax. That's the goal. But can we, again, use the physics in a smart way? So this one's a little bit more involved. This is a paper we published in 2022. So we're gonna go back to the physics of my wind structure model. I wish I had put this on here before, so now you actually can see the angular momentum structure associated with the wind model. And I guess a key point on the physics side is that everything starts from the outside and goes in. Air is inflowing and trying to bring high absolute angular momentum air in. And so what this is showing is, so you have if you say you're at the radius of 34 knots and that air gets to the radius of maximum wind, it has some higher amount of angular momentum, and then it's lost a healthy chunk of it due to friction. Otherwise, it's conserved. So there's nothing to say. It's just how much do you lose to surface friction, and that's implicitly what my wind model is trying to predict. So this is how the storm spins up, why it spins up as it goes in. But it's really this jump from here to here that's important. And so what I want to do is, again, instead of just doing a simple empirical model, is to think about this physically. I'm going to take advantage of the physical relationships that are in my wind model. So what we're going to do is this is in 3 steps here. And so you have your radius of 34 knots, radius of 17.5 here, and you can calculate the angular momentum there. And then if you knew the fraction that you have remaining, so you start with some angular momentum here, and then you lose some fraction of it, and then you end up with what's remaining at R max, and then you can back out from the definition of angular momentum the radius of maximum. So these 1 and 3 are just the definition of angular momentum at each point. But it's really the middle part, which looks silly, is what is this? What is this ratio? What is your fraction? And then how does that vary? And so this is where we'll try to use what my model says for that as a starting point. So let's see here. Oh yeah, okay. So the idea is, let's see, I guess I skipped a step here. Hold on, I have this out of order, or there's hold on a second. I'm just trying to see. Okay, I guess I skipped exactly how we get to this. Oh no, never mind. Okay, now I remember why I'm doing this. Okay, this is a little bit more complex how we put this together. So this is the form that we use. Let me go through this. This is the form of the equation that we use, which looks more complicated. It's a logarithm of this ratio, which is you can take the exponential. This is a Poisson regression. So the thing we want to predict is equal e to the stuff on the right-hand side. But so this is a linear regression in the log of what we want to predict. And then I have these specific predictors in this form. And so why am I doing that? This is the part where the theory really comes in, and the F and the R are combined together again. So why? Let's see if I can try to motivate this form. So this is what the theory says. This is where I skip this step to say that in my model, this ratio is dependent on the maximum wind speed. And then again, it's I have the 1/2 here, but it's F times size. So in like angular momentum worlds, F and size are always together. And I guess in the pressure deficit world also. So they're always together. But so my model, the theory says, again, that size and latitude get combined and then get intensity. And it's just intensity here. And so this is the distribution of this ratio. So, which is not linear. But so with lower intensities down here, lower intensities and or smaller sizes or lower latitudes, you can serve a larger fraction of your angular momentum. And then as you move up towards the blues, you're losing a larger and larger fraction. So when you get up here, you've lost 90%, 80-90% of your angular momentum.
How did you come up with that exact?
This form, I will show you why. Yeah, so why this form? So where does this come from? So this is where I used to call this a human learning approach instead of a machine learning approach. This is chosen for very specific reasons. So why this is a positive definite quantity. This fraction, it's going to go it's bounded between 0 and 1. This is a place where physics is nice. You're now trying to predict something that can't be less than 0, it can't be bigger than 1. And so since this is positive definite, we'll use this is where but it's close to 0. A logarithm is nice. That's a common thing to do a Poisson regression. So for intensity, well, we have a lower bound on intensity. Is that I don't have a radius of 34 knots if the maximum wind speed is less than 34 knots. So why do we choose not? Why don't you just put Vmax in? Well, it's nice to subtract off this quantity so that if basically you have the weakest storm possible, you're going to have that'll be 0. So that's why we choose that. And then why this? So why not just use this term alone? So this is chosen very purposefully. So what I've done is multiplied the size and radius term by this intensity term. And so why is that? Something that you can see in here. So the dependence, what this is saying is the dependence on this is amplified at higher intensities. And so you can actually see this in the theory, is that if you go left, so if you go to the dependence on the size and latitude is going left to right, on the x-axis, along the x-axis here, notice that the colors change very slowly. So the dependence is weak at low intensity, but then as you go to higher intensity, the colors change fast. So the sensitivity is much stronger. So I'm trying to build that in. So that is why it takes this very, very specific form. So this is a place where I'm trying to capture something that is fundamentally nonlinear and see what that looks like. So that's how that's the design for this. Let's see if I can. So yeah, so this is just better than a simple linear model. And you can actually do, it's been a little while since I thought about this, you could do, again, tests where you do the parameters separately. And I tried all sorts of different versions of this model, and they're never better. So this is the simplest model that's also the most powerful. Adding more terms or doing things in more complicated ways is not going to be as good. So again, this is for capturing this theoretical dependence. So yeah.
You come up with this equation from your wind model.
So the wind model, so this is calculated numerically from my wind model, and it says, well, so analytically, the wind model, yeah, I guess I don't have this, but analytically, the wind model says that this ratio, the angular momentum loss ratio, depends on Vmax and depends on this combined parameter. There's not an analytic equation for that, though. It's just that those are how the terms appear. And then what I do is numerically calculate that for just all values in this space, and then this is the distribution that you get. So this is where I don't have an analytic expression from the theory for this distribution, but I know that these are the two parameters that are in there. So does that make sense? Okay. Yeah. So yeah, this is part of it. It's like, this is really messy. I don't have an equation to write for this. And again, it's theory. We don't theory is messy. Maybe there's assumptions in there we don't want to think about. So let's see here. Oh, I guess this is the same thing. Maybe I should have switched this and shown this first. So, okay. So I want to emphasize here is this transition from these values are, you get high, or you have high fractions here, so you conserve more of your angular momentum here, and then as you go to the top right, you conserve a lot less, going from something like 0.7 down to 0.2. So that's what the theory shows. It's very nonlinear. I reversed these. I should have shown these slides first. Yes.
If you look at the vertical direction, so if you fix I suppose, the size.
Yeah.
And then for larger size, you would have a monotonic behavior as you move up the Vmax. But for small,
Yeah.
I suppose, and it's not monotonic.
It is not.
Why is that?
I have no idea. I had thought about it for a while. I actually can't remember now if there's any evidence of that in the data. Maybe I'll show it because I haven't presented on this for a few years. No, yeah, this is weird. You're right. So as you go up this little place, where suddenly you think the dynamics change at really small size and latitude. And I think I'll get to it and see. I'm pretty sure we just don't have any data, so I don't know. And I don't even really remember. I spent some time trying to think about why it's happening, but I'm not. This is where maybe it's not meaningful. I'm not sure. So yeah, I'm glad you noticed that.
In your theory,
Yes.
the junction point.
Yes.
Yeah, and I was wondering if it's usually inside R34 or outside.
Usually, it'll be usually outside as long as the intensity is reasonably above 34 knots. So, because technically R34 knots gets close to R max when it's really weak. But once, yeah, it's a good question. I don't know exactly when the transition is. I would guess it's probably once the intensity is more than 60 knots, it's consistently outside the transition. I don't know exactly.
So basically, this fade out, it shows the dependence based on values in a form theory.
Yeah, it's a good point. Mostly, but not entirely. So like actually here, let's just go back to here. This one's a good, wait, do I have a plot of my model with the junction point? So if I do, there we get back to this one. So here the transition is probably around here. So this is pretty far out here. So actually R34, so it's both. If you're intense enough, it's both partly outer and partly inner. Yeah, good question. So let's see here. Okay, so now, I think I mixed these orders. So sorry, but I walked through. Hopefully that made sense. So let me go back. So in the end, then we're doing this. We've set this up, and now we just do the regression model on the data. And let's see here. Oh yeah. Okay. So first, actually, no. So we can back up before we do any regression. Let's just look at the data in the same space. So do we even see this? We wanted to see yellows and blues. And so what's cool is this is very, let me flip. So here was the theory. So we have, I can calculate this everywhere. We get the weird section up in the top left. But without even, I love for models, empirical models, I guess I didn't do this for PMED, is to, don't even do the regression, just like plot the data and see what it looks like. And so we wanted to see yellows down here and then blues. But so what this shows you is you can first see that, but you can also see what part of the phase space is actually sampled. So we don't have data way over here, and we don't have data up here. So I don't know if it's real or not. Maybe in models there's a way to test that. But we see this general progression from these yellows down here up towards the blues, but this is in pure physics land up here. Maybe in the Western North Pacific, there's more data this way because you have really big storms. So I think this is sandy here, if I remember correctly. So, so just say by eye, we're getting something that, like at least first order has something that we expect to see. So, so that's nice. And so when you do the model fit, now you do the layer regression model. Let's see which, I guess the next slide I have the numbers, but this is what you end up. So it's not exactly the same structure, but we're capturing the first order nonlinearity, which is by design. That's how I designed the model. And so when you do the empirical model, the regression model fits the observation. This is the pattern you get, which is what we wanted to capture. We could. So okay, so what does that look like? So this is the actual equation. I've written it now instead of the log. I've made it an exponential now. So this is where it's a log linear regression. So we get this equation. And I guess maybe I showed you what the results look like. The dependence is what we wanted to see, is that you have larger, lower value as you go to higher intensities, or you go to larger sizes. Or larger size or higher latitude. So so this is the case again. Physics gives us the predictors, and in this case, there was some thinking about how to do the physics. This wasn't fully the physics telling us. Like for pressure, I had an analytic equation, so I was able to literally use those. In this case, this was a little bit more of like, okay, we know what parameters matter. I actually don't have a solution that says it should be this to the third power or this, that's all I have is that this is in there and then this combined is in there. And then just based on the structure, tried to come up with a model that would fit. So, okay, so now let's just look at the comparisons of the data. So we'll walk through this again. This is a similar type plot to before. It's just bins now instead of all the data points. And so this is observed radius to maximum wind and then the predicted data. Let's see here. How did I say? Yes. I skipped this over. Let me go back. Is just to note here. So this is where, in this case, we're just using extended best track data. So we don't have this issue of we didn't try to center it on any observations or anything. And then this goes back to John Naff for a long time has always felt that south of 30 and west of 50, which I should have said this before too, is where we pretty much always have aircraft reconnaissance. So we just feel good about all of our estimates of the data in general. Like anytime a tropical cyclone is in this region, it is a threat to land. And so the Hurricane Center, we have the fortune of being able to send airplanes regularly. So in this case, though, we're just using extended best track, limiting us to what I just call a high confidence data set where we think we have pretty good estimates of all the parameters that we need. So So yeah, so now that's where that is fit, and that's what gives us these coefficients. So yeah, going back here, so observed on the x-axis, predicted on the y-axis. The 1-to-1 line is here, and then the conditional median is this gray line here. So we can see how the errors vary, and then the colors denote the what is that? I guess this is the relative sample sizes. So the darker colors means more data. So you have lots of data down here, and then it spreads from there. And so there's an interquartile range and a 5 to 95th percentile. And then what I fit on here is a best fit line to the conditional medians. So trying to not overweight all the data down here. And it's important to note when you get down here, radius to maximum winds has an implicit probably, like it's measured, it's reported in 5 nautical mile increments. So there's like an implicit plus or minus, I guess 2.5 or maybe 5 nautical miles. I'm trying to think. There's an implicit uncertainty when you get to really small values here. So, so you'll notice, so there's, in general, the model does a pretty good job. There's some systematic bias here. It's actually, I put the line all the way down here, but these, again, in this area here, these errors, these biases are small relative to, say, 5 nautical mile increments. So it's really something when you get up to around, say, I don't know, maybe 80 to 100 kilometers. The bigger RMAX is where now there seems to be some more systematic underestimation. So these are the weaker, generally would be the weaker storms. But so there is some systematic bias. Yeah, but so the RMS error overall is about 20 kilometers. So that's across all data. So let's see here. Oh yeah, so I just said this. This bias, you can do a simple bias correction. So as I'll get to later, and I have a code for all of these models. And so I just do this bias correction just for these big RMAX values. Just to note, this is something in John's space. I'm not sure if any of you have worked with these, is that we compared it against our model and a true out of sample test against a few other methods that I'm not gonna lie, I don't know full details on. These are both satellite based. This is IR based, and then I don't actually remember what NAF 2015 is. But our model does a lot better than these other models. So and then there may be other models for RMAX. These are the ones John uses. So he was very excited that our model was a lot better. So so there are different types of information that are going into these models, to be clear. So it's not, I don't know if there's anything to consider for that. But so it's the place again. You can also try it in the high latitude regime for that smaller sample size, and it does a pretty good job. So using the same model, but just applying it to data above 30 north. So and still, it's not bad. It's got much more variance, unsurprisingly. Again, and I don't know if RMAX, when you start to get really asymmetric, what RMAX means anymore, but we have the data for it. The other thing that's really cool that I like working with these models, again, is you can do experiments. So one thing that had been noted for a long time is that RMAX tends to increase as you move poleward. But we don't really have an explanation for why, and so we can actually use this empirical model. And so we walk through what this is showing. So latitudes on the x-axis. There's we have Vmax as a function of latitude. These are just median as a function of latitude in our data set. And then the light blue is Vmax, and then the black is radius, different radii. So Rmax tends to increase. You notice the Vmax actually doesn't really change that much with latitude, the median. And then, but R34 knots also tends to increase with latitude. So, so what we can do is take our model, and I think if I remember this, we just took the median values of each of these. I don't think it made a difference. Or actually, maybe this is the overall distribution if you did it for every case. Just showing how it compares. So we do a pretty good job of predicting the median Rmax as a function of latitude. And then what we can do is do these different experiments. Okay, so these are the ones I'm fitting to the medians, but then you just turn on or off the variation in different things, at Vmax or at latitude. So you can test, we have 3 things we think matter: latitude, Vmax, and then our 34 knots and see which ones actually matter in driving this increase in Rmax. And so for these other experiments here, nothing really changes. Basically, the slope as a function of latitude for Rmax is not very sensitive to variations in Vmax or the variations in latitude itself. And so it's really suggests then that it's really just the outer size that's driving the increase in Rmax with latitude. So that is our maximum. So let's see here. So let's pause there, see if there's any questions on that. Otherwise, the third part of this.
Hey, do you have any question or comments?
So we go till when? Till 12?
The 12:30, but
Okay, cool. So, all right, this will be perfect. If people are hoping to learn about size expansion theory, I might have to just send you some papers. So, we'll see. If we have a few minutes, I can at least give you a little bit about it. So, I want to end on this part, which is great. So, if you have a question. Yeah.
The last slide,
Yeah.
you're talking about the relationship between R34s and Rmax. And are you talking about some physical causal relationship between R34s and Rmax, or this kind of statistical?
I guess at this point, both. We've tried to bake in the physics. So if physically we expect Rmax to, like if you increase R34 knots, you should cause an increase in Rmax. If you increase Vmax, you should cause a decrease in Rmax. But then in this case, we're testing it empirically, is that we have built in those relationships into the empirical model, and now I can basically just test the sensitivity of Rmax to each of those terms. So I'd say kind of both. Both, yeah. Like it's causal in this extent that you believe that the model I've developed that's baked in physical relationships. But at the end of the day, it's an empirical model but based on physics. So.
I'm wondering how can the outer structure and R34 model determine influences the
Yeah, so this is something I kind of wish I had said this. I used to emphasize, so I was going to go back to this, is like the physics of this, which we haven't talked about, the radial physics, is everything, there's inflow. So like every inflow communicates stuff from the outside in. So if you reduce the angular momentum here, and I've actually always wanted to do this, I've never tried, it's like to make like a time-dependent version of this. If you put in a perturbation, that will get transmitted inwards. And in the matter of like from R34 to Rmax, I guess I'm trying to think the inflow, I can calculate the inflow velocity is probably on an order of an hour or two, I would think, to go this distance. So yeah, so all the information comes from the outside in. So it's all, as you go in, it's air is coming in to the boundary layer from above or from outside, and that's all being communicated inwards. And so that's the thing, it's like this, like, it's not, this doesn't control this. And it's even important to remember, like, this is a small area and this is a huge area. So the air is converging inwards. And so things that happen out here matter a lot for, like, the inner core will feel changes in the outer core, in the outer circulation, yeah. So yeah, that's something, I wish I would emphasize that, is that there's a direct, just simple physical linkage to the outside matters.
I understand your view.
Yeah.
And inflow from outside is very important to determine the inner structure. For that case, there is the Vmax also may change due to
the average circulation?
Yeah.
That's a great question. I would say no. I think Vmax is, all of our theories for the physics of Vmax basically don't care about anything except what's happening right below the radius of maximum wind. So that's one thing that's very strange. I haven't talked about Vmax at all, and part of that is that like all of our potential intensity theory, there's actually newer versions that are simpler. We have the Carnot cycle view, but actually in a paper that was sort of lost in 2019, Russo, Rizzi, and Emanuel, they derive a version of potential intensity that makes no assumptions, and all you care about is what's happening at the radius of maximum wind, and that's it. It's just the surface fluxes at that point. And so Vmax in my mind is like its own universe, and then the entire rest of the structure. And that's, of course, in reality, the angular momentum has to come from somewhere. So I guess I should be careful. I don't think about Vmax as caring about anything else. But of course, like this is where when you get into real modeling, like you have eddies and other things, like the angular momentum does matter. Like that has to come from somewhere. So, but weirdly, all of our theories for Vmax, which work very well, don't think about any of that stuff. So yeah.
So just so related to his questions, I might be wrong, but just correct me if I'm wrong. So based on a conventional understanding, maximum wind speed is determined by environmental condition, right? Based on the Fermat-Perrier manual theory. In that sense, R34 is determined and Vmax is determined, and we consider the inflow transport to the inside. Of course, Rmax is depending on the outer radius, right? So if the other outer R34 and Vmax is determined by environment, in that case, okay, they should be related. I think that is, conventional, my understanding. But as you mentioned recently, MPI theory should be considered as a very local growth dependency, right? So there's a local change of for example, equivalent potential temperatures within, and it is determined by not whole environment, but also it dependent on very local properties. So I think still arguments exist, but it's kind of recent stuff, I think. Right? Is that
no, I agree. Yeah, no, I think of Rmax as whatever. If you have a size, an outer size, and you have a Vmax, Rmax is like, or you have an outer size, then you have a Vmax, and Rmax is whatever the structure tells you Rmax should be. Like it's not meaningful in any particular way, other than that's just like, maybe if you have an outer size. Once you know Vmax, that tells you, well, how far in do I need to go to hit that Vmax? And then that's where my Rmax is. And that's how I think about it. Like it's not, Rmax isn't special on its own. It's just like an outcome of size and intensity.
One thing I cannot understand is, yesterday you showed the correlation between the Rmax and R34 is not so high, right? About 0.
Within the door.
Yeah, within, or like even inter.
Even
0.3 or something like that. So in that case, maybe we need to consider other things, right? It is
I mean, I think this is where I haven't revisited that. It'd be interesting to think about that again. And that when we did that, I mean, that was when I was in grad school and I didn't really know anything. I mean, now we know latitude matters, so like I don't know where latitude fits into that. Yeah, I think you'd have to, there is a very naive, just take the whole database. Like, I think I wonder how much better the correlation would be if you were careful about picking like, a subset of tracks that are all really similar or something like that. So, so no, I think there's other things going on. I think some of it we now understand better. But then of course, there's also just real variability too. I mean, nature is more complicated, so yeah. Cool. Any other questions? Yeah. All right. Last section here that we'll go through fully, which I'm excited about. I told you all about this wind model, and now let's not use it. So this is work with Dan Tao, who I mentioned earlier, Robert Nystrom, and then Arthur Avenat, who's been working with SAR, which we got to use some SAR data for this, which is awesome. So, okay, so old model, we're going to put you in the grave. I've told you all about this model. It's great. It's really cool. It has lots of cool properties. Why is it not good? It requires numerical solvers. So the code, it's actually like 1,000 lines of code. I do have it online. I'm happy that you can access it. It's publicly available. But it's annoying. It's slow. It's hard to use. It's really a mess if you dig into it. And then the big thing is it imposes a very rigid relationship. It's not saying that this slope is constant, but it's actually the M max over M34, the angular momentum ratio. It's just it's rigid. And in Tao et al. 2023, they showed that basically it doesn't predict enough variability in the slope in here. compared to, they looked at simulations and observations, I think, and there's just more variability in there in the inner core. So, okay, so wait. Actually, the other thing I'll say is that also in operations is that what if I have, in this case, this model can only take one radius, but maybe you have two. Like maybe I have Rmax and R34 naught. If I take my model and you fit it to R34 naught, you might get an Rmax that doesn't fit your data. And then you might say, well, this is annoying. What am I supposed to do? So you want to actually allow for a little more variability. So I'm hopping right into this theory, which is really cool. So Dan was the one who led this. And so how do we put these things together? So I'm going to show you, I can't show you everything. There's one very cool thing that I was excited about, but just stepping through the first, it's really a different component. We talked about how it wasn't really modeling the eye. We just do a simple linear eye model. I think there's probably some room for a proper theoretical eye model, but I think in practice, I don't know, outside of meteorology, I don't know that it really matters for practical purposes to get that exactly right, but could be parabola, could be linear, we just did linear. And then, so what they did in their 2023 paper, they proposed a new model that basically allows for, I'm skipping some of the details here, but it's called linear M-slope. They call it the slope model, which is just that they noticed in simulations and in data that the angular momentum profile between here and here tends to be very linear, but its slope can vary. And so they just proposed a model that ends up, you can translate it into this equation for wind speed as a function of radius, where you have a slope parameter for the rate of change of angular momentum between the 2 points. And so this is their linear slope model, and it gives you something that's going to look, it's not modified Rankine, but it's something like that. So I showed the data before that modified Rankine can work quite well. But then they choose this model, and then they actually, and then we transition that to a modified Rankine in intermediate. So we now have like an intermediate model that actually brings this, and I could put on here, I think this brings the profile out a little bit farther, which is better, closer to observations, as I'll show. And then when we get up here, this is my model, this is the outer wind model, but an analytic approximation that took me 15 years to pop into my head while I was on a run in a forest. And it's actually remarkably, I would love to go through it with you, but this equation, if anyone has spent any time thinking about this equation, I have spent so many times in my career trying to come up with ways to solve this. And then realize something very simple, which is that you can actually, I don't know, I'm not going to go through here. I can't. It's, if you want to talk about it, I'm happy to talk about it. It's a very simple mathematical trick. It's not even anything fancy, but, and it gives us an equation that's very similar. And so this is, in the end, let's see here. Yeah, so this is the equation. So I'm not going to step through the math or anything, but the point is it's all analytic. These are the equations. And what's cool is that the part that you don't see is that the math works out where these get merged automatically. So you're not picking the merge points or anything. So you have the I, and so in this case, you have both Rmax and R34 knots. So if you have 2 radii, then you connect this point, and then actually the rest of the equation, this is designed so that it's basically a transition from something that's concave up, and then it comes over here, and then it transitions at these points. And these are predicted internally. There's unique solutions for this. So this is where the inputs, this is adding a new input. It's allowing you to input Rmax, which is really nice if you'd like to use that. So now it allows for variations in here. If you have Rmax and R34 naught, you're not constrained by whatever my old model says for how that should work. What Dan and Robert were doing was comparing these to simulations first and then to data. So this is just their simulations. And so the black curves are the simulated wind profiles. And I think this is just for one storm intensifying. And so actually, this is the really nice one to highlight is like, let's say you have Rmax. So my model, I've been doing it from R34 knots, but if you did it from Rmax, let's say you have that here. My old model is the solid pink here. So, and you can see is that like, it's gonna be biased high, in this case, at all radii. And this is really, this looks like it's the bias is at all radii, but it's arguably, it could be the reverse. It's like, maybe if you just moved in Rmax, or if you'd fit it down here, it would have gotten everything right, except when you get to Rmax, it would have had an underestimate of Rmax. So if you shifted the pink curve to the left a little bit. So this is part of the problem with my model, is it's just too rigid. And so if you have an error in the relationship between any two radii, like R34 and Rmax, it may propagate to the entire profile. You're just going to be biased. You don't really want that. So, and in contrast, the dashed pink is, let's see, oh no, the blue is the new model. I don't remember what the dashed is, sorry. I'd have to go back. The solid is my model, and then the blue is the new model. Of course, to be clear, it has one more parameter in it, so you know you hope it should be better on its own. But it's really just about like clearly my old model had issues with correctly capturing the full structure. And then additionally, what I think is really awesome, so those of you who work with SAR, synthetic aperture radar is really amazing. It's the first time. So I worked with QuickScat data for a long time. That only works up to about 30 meters per second, and then it saturates. And until SAR, all of our remote sensing platforms, space-based remote sensing platforms, could not really see through heavy rain. And sometimes clouds, but usually heavy rain. And SAR is much better at that. And it does not saturate as far as we know. I'm not a SAR expert, but this is my understanding of SAR. So here's an example from one of Arthur's papers using SAR, where you see a SAR pass gives you really an incredible view of the full wind field, near surface wind field. So, and so here are just a whole bunch of profiles. We went through it systematically. We had a whole database of, I forgot how many hundreds of profiles from SAR. And just comparisons of each of them for different cases. The black curve again is the SAR profile, and then pink is my model, and then blue is our new model. Just showing you how you can see sometimes like here my model is pretty good, but then here it's low biased in a lot of places, or here it's low biased, and then here it's a little off. Here it's high biased. It's just like it's too rigid. So this now, the new model now we can better capture inner core structural variability, which I think is really nice. So yeah, there's lots of cases that look pretty good. I think statistically, across all the cases, this is just the mean bias between our model and the SAR observations, and then the RMSE. These are both as a function of radius, distance from the radius and maximum. But yeah, just we weren't trying to fit the eye itself. So it just does, these are pretty good statistics for comparing with SAR. So that's putting all the pieces together. And I just like to, this is now stuff I had code for. So the idea here is, can we go all the way from using these models from operational data? So maybe you have, again, this is for North America, you might have an intensity of 100 knots. You might have a mean radius of 34 knots of 200 kilometers, let's say. You're at 20 degrees north. So you have a data point for maximum wind speed, one radius over here. So that you could, if you also have Rmax, you could plot that on here. Or if you don't, you could use my Rmax model and predict Rmax, the observationally constrained one. And so maybe you do that. And so my model would say, it's 24.5 nautical miles. And so now we have a data point here and here for Rmax and our 34 knots. And so as part of this, you need to calculate in my model the translation speed. And then with all this, you can now calculate, if you have the outermost closed isobar pressure, you can calculate the minimum pressure. And then you can combine that with the wind profile model. And now you have a wind profile model. This is our new model shown here. And then what's nice, the last step that I actually haven't said is this is the part where to do the pressure profile, you can start from the prediction of minimum pressure and then integrate your pressure curve out from there. So if you just do gradient wind balance going in on your wind profile, you may not match. You may not hit the right pressure deficit or the right minimum pressure. So this is where having a model for the minimum pressure, now you can basically use gradient wind balance for the structure, but have it so that it actually hits the right pressure. So yeah, this is putting all these pieces together, which has been really cool and really, I guess I put this here. I started, there's a Python package for all this now that I created called TC Wind Profile. I just updated this 5 days ago with the new model because I should say the wind profile, the new wind profile that it's in very minor revisions. I don't know why they haven't accepted it yet. We've been waiting for a month, but it's in GRL. And so I was waiting for us to get past enough revisions where it was like, okay, this is going to happen. And so, yeah, so this is all of these pieces are now in this package. It's not necessarily, it's set up to do everything. So right now it's set up where if you just give it our 34 knots, it'll predict our max, but I want to update it so that, you could also give it 2 radii if you had both of them. So there's some things I'd love to do with this, but just right now it's on here. It has a DOI. It's on the Python package, PyPy. And it's been really cool to be able to put all of this stuff together. This is where getting to come here, getting invited to come here is just really great timing because this is something, different pieces of things that we've been doing for the last decade have really come together in really the last few months even. And so it's been really fun to be able to put all of those pieces together. And then now I'm really trying to make it useful for people. So this is something, if you end up using it, feel free to email me. Let me know if you have any problems, the code broke, something like that. That's helpful. Or if you have ideas of, hey, I want to change this in the code, that'd be awesome. Love to have people help and we can make new versions of it. So that's all these pieces together. So I think I'll pause there or maybe stop there. We can just discuss. You talk about expansions later if anyone wants to. So maybe we're close to noon. So yeah, if you have any questions.
So my question might be beyond your interest.
Sure.
But my question is related to the wind radii in each quadrant.
Yeah.
And each operating perspective here is increasing demand for the wind profile information and the forecast.
Yeah.
And do you have any thoughts on how to expand the model to the
requirements? Yeah, I do. That's another thing I'd love to do, or maybe somebody can help me do. I think the easiest thing is to add in wave number 1 asymmetries for motion and for shear, because we know that right of track, usually right of track and then a little bit rotated is where you have a asymmetry and then a shear induced asymmetry. I've never worked with those explicitly, but I know those are the most natural thing to add, and that would give you quadrants. I will say, if you had an operational estimate, the track alone. So in operational mode, you know the previous track, and you could estimate the current translation speed. And if you have a forecast of the track, you can calculate translation speed, and then you can also, if you have shear data on the shear, you could calculate the shear vector and then add in a wave number 1 asymmetry. I think that's the easiest thing in terms of I know one thing that I realized has come up is that you don't want to do the profile fit to each quadrant because actually there's no reason the hurricane doesn't spin like a solid body. If the inner core spins really fast and the outer circulation spins slower. So they spin, this one goes really fast while this one's the air is going around very slow. So there's no connection radially within a quadrant. So you don't want to do that. But yeah, I think that's the easiest is adding a wave number 1 asymmetry. And beyond that, I don't know. I think, I guess it depends on exactly, if you're trying to get to finer grain details, maybe there's some cool creative things you could do if you have more. This is where the more information you have, the more options there are. And so, so I'm often thinking in the simple, trying to keep things simple, but for operational work where you, I don't know, do people want high res wind field information? Is that what you're thinking about? Like,
Yes, for example, take advantage of the observation from SAR.
yeah. So that's where, like, I can imagine, for example, maybe this is the thing that pops to mind is, let's say you had a SAR pass, but it only has half the storm. You could probably take that data, fit the wind profile model, and like basically use it to model the part you don't have, for example, where like you could use that data intelligently to come up with like estimate, like do something to estimate the wave number one asymmetry and then like interpolate so that you have or model the part you don't have. Like that's one thing that comes to mind. Obviously, if you just have SAR data, you should just use the SAR data. If you really just want high res everything. So yeah, that's my thought. I think there's a lot that could be done. A lot of stuff I don't even know, but I think it's just once you get to real world, the real world is obviously much more asymmetric and there's more nuance, more detail, but then you also just have every day is different in terms of what information you have available. So yeah, I thought about just at a general level, like some sort of data assimilation type idea of like, it would be nice if you could take my model and just throw anything, like, and combine the two somehow to say, here's the best guess of the wind field. So, but that's one thing I haven't been involved with much, is like a proper operational analysis. So, yeah.
Comparing your model with SAR observation, the SAR is observing surface wind, so the surface wind is can include not only tangential wind but also radial wind near the surface.
Yes.
So in cases of underestimation
Yes.
of your model, in this case, you can explain the reason by the.
It's possible. I like that. You're saying my whole model? Yeah, I mean, sure. I think that's a good point. I think that's the only limitation for SAR, is that it doesn't have direction. It just has speed. And so that's actually a really good point, is that in principle, this is part of why I like to just use the surface data directly instead of worrying about anything else, is because even the surface observations, like if you, in principle, let's say probably out here, 90% of the wind speed is tangential and 10% is radial. But so that means, like, if you assume that's constant, that ratio is constant, or then you're just, you're off by a factor of 0.1. And then you can adjust that, and then maybe the wind profile model will look exactly the same. Just like everything would shift down. But in reality, that's probably not true. So yeah, I think that you could explain any discrepancy between the model and observations in that way, and say, well, here's some assumptions that go into the observations too. So that's why I always want to trust the ops first. But yeah, you're pointing out actually that in this case, it's not technically an apples to apples comparison. Like when I did with QuickScat data before, I had direction, so I actually projected all the wind vectors onto the tangential component, which is much more precise, I think. But here, like actually that's where, SAR data, when you get out here, like this is where if you look at wind speed magnitudes ever, they'll never go to zero because there's always random movement. But if you look at the tangential part, they really will go to zero. You see this in models too. But so anyways, I guess, yes, that could explain it. Maybe my model is better than I'm selling it for, but I think this is where between uncertainties in the theory and uncertainties even in the observations, I don't know. Like to me, I want to think of SAR as the truth as much as possible. So yeah.
I'm interested in how many degree of freedom is left. Like for example, if you put 4 parameters, 3 marks are 34 trapped in the environment.
Yeah.
How many?
What do you mean? How many degrees are going to be left? Like in this?
Yeah, like I was wondering if R counts is a free parameter or it's directly solved, like analytically solved.
Oh yeah, no, it's all analytic. That's all implicit. So this is, I'm not doing literally. You don't. So I should be careful. There are a couple of other physical parameters in. Let me think here. I guess actually I'll just put the equations up. In here. Yeah, so I skipped. Hold on a second. Yeah, hold on a second. maybe A has, I forgot what A is. So this outer model has the radiative subsidence rate and the drag coefficient in it, which now I'm forgetting. Is that in A? It can't be A. This is now I'm really confused. I'm gonna have to go back and look. The transition points are implicitly predicted. You do have to, so like here we chose -1. So like technically you could change that. But this works and it's just the simplest. So that gives you this curve. So there are things you could tweak if you want to, but the transition points, I'm actually not quite sure. If you change like the exponent, it'll like the transition points are, well, actually this transition point is the radius of 34 ounce. So these 2 points you have data for, but then this point is you don't have to define because there's only one place where the solutions are smooth across the transition. So the model.
There's no like fitting procedure.
Yeah, so there's no fit. That's the thing. It's like, so I'm a little confused about why this equation doesn't have under the A. I forgot what A is. A must have. A must have so the outer model has a couple of physical parameters in it, but otherwise, yeah, there's no. That's what's beautiful. It's like there's no degrees of freedom in this. Like this is implicit. It's given the constraints that you input, it solves for this point. So yeah. Does that make sense? Oh, yeah.
Any other questions or comments?
Yeah.
In this model,
Yeah.
the Rmax is an independent input parameter.
Yes, you have to know our max.
2015 model. Even 2015 model is Rmax is predicted from Vmax and R.
Correct.
So it's very conceptually different.
Yeah. But that's where, so in the code as I set it up, is that this is a case where if you have both of these, you can use them. But you can also if you have this, you can predict this from my Rmax model if you didn't have this. So you can make it conceptually analogous by saying, I'm going to use the same inputs as with my old model, but I'm going to first predict this from my new empirical model. So like, does that make sense? It's like my old model would have predicted this for you. Another option, this model now lets you have both of these. And so you could use my model to predict our max from our 34 knots if you want, and then now do the model. So it's more flexible is what I would say.
And in the comparison with SAR, and in the next slide, for some case, the blue and purple line is very different.
Yes. And that's part of this is like what the blue line is doing is it's getting this right. It's going to get the structure in here on average right. Like it doesn't, there's places where, like actually this is a good example. We're here. There's a little bit of there's 2 Winmax in here, so it's even kind of a weird one. But it's gonna link Rmax and R34 correctly here. So whereas my model doesn't have any actual relationship between 2 radii that constrains it. And so this is like a really good example of one where it's just like it clearly gets the general shape right. But depending on where you fit this model, like I guess I could give you examples. It's like if I took my model, I could fit it to here, and it might get this right, but then go off inside of Rmax. Or if you fit it to Rmax, it ends up being too large everywhere. So it just doesn't have a way. I should say it does have a parameter in it from the inner core theory that can change the width of this, but it's just totally arbitrary. It's the ratio of the exchange coefficients. So like it does technically have a way you could change the width of the inner core, but it's there's like no reason to do that. So yeah, so this is the point. It's like the way it's set up, you never know if it's actually going to get this linkage correct. And so maybe like I think on average it does, which is why it works pretty well. But there's individual cases it can be really off. And so this just lets you be able to capture that better.
So for example,
Yes. Yes. This is one. You guys can tell me, I don't know why Hagibis was really bad, right? That was the one that hit Japan, right? I don't know, I guess this is just a really weird shaped profile. It has a really small Rmax, but then like, so I guess it's not a super strong storm. I don't know which passed the time. You guys would know better than I do. Yeah, but so this is a place where it's like really bad. And to be fair, these are weaker storm. This is a weaker storm at this time.
Near landfall.
Is that near landfall? Okay, yeah. Yeah, so I don't know. This is the kind of thing that can happen. Like, at the end of the day, the inner core variability is greater than what my model allows for. The inner core structural variability. And so it's just like, if you want to be able to capture that, you need a more flexible model. So yeah.
It depends on station. I mean,
it could, yeah. So that's a separate question. Because in this case, we're just saying, what Dan showed in the previous paper, like we didn't do any analyses of why it varies. We just showing that like, hey, there's a lot of variability, and so this model can capture it. But it's a great question. They, in their 2023 paper, they looked at like during intensification was their focus actually, which I think was like this is a good example of one where I think they were finding that like even just in a model simulation, during the process of intensification, the slope of the angular momentum structure changes in a way that my model doesn't allow for. And so they wanted to have a model to represent that. But I'm trying to remember if they looked empirically and across observations as well. So in this case, we haven't done anything about the why. Like why does it vary? It's just there's more inner core structural variability outside of Rmax that we would like to be able to capture. And so this model is just able to do that. So that's a good question. And why?
thank you.
Yeah. Okay. Okay, yeah.
Furthermore, they achieve travel around the Japanese island, interact between those regions. So
Okay.
maybe the middle indicates the percentage values.
Oh, here I see. Yeah. Oh, yeah. These are all heck.
Maybe the changing to interaction between the not between.
Okay. Yeah, because this is where this is where I just put this on here. I didn't realize. Yeah, this is earlier Hagibis. So this looks more like a regular profile. Like mine is still biased, but it still looks more like a tropical cyclone profile. And then you're saying here is the concentric eye wall. And then here, this is to have a radius of 34 knots of 300, almost or 400 kilometers, but then the radius of maximum wind is small, is weird. I know. So yeah, that's not. I don't even know what to think of that. So you're saying it's maybe extratropical land interaction. Okay. Yeah.
Okay, so any other question or comments? Okay. So you mentioned that if one to use your RMAX model to take RMAX, and so that will make your new model takes in the same set of predictors as your old model.
Yes.
Now, I was thinking is how much difference will that make? Because ideally, if you have trustworthy RMAX, that using your new model gives the best estimate.
Yes, I would say if you have RMAX that you trust, then
in other words, how sensitive is your new model to the RMAX?
This model, if you, it's not really, what's nice with this is if you move RMAX a little bit, it's gonna just connect the dots basically. So, it's a good question. That's where my old model, when you move RMAX a little bit, the whole profile moves. And so that's the problem. And in this case now, if you move RMAX, the curve will just, tilt a little bit in the end. So, I don't know if that answers your question. is like, how does it, in my old model, everything was sensitive to Rmax. And here now it's muted that sensitivity much more to make sure you're not changing everything already. Is that what you're asking? I don't know if that's still a little bit off.
It's okay, because I was thinking, yeah, I mean, it obviously your new model will not reduce the old model even if I take away that
Right.
max in a sense that the max model.
Yeah.
From the alpha before. But yeah, so what yeah.
Yeah, I see what
So
you mean.
just to clarify that.
Yeah. Yeah, I guess the way to think, if you took my old model, the full model, and predicted our max from our 34 knots, then this should give you something, I guess I haven't tried, like, this should give you something that looks pretty similar. But that's the point, is that that's
Not necessarily, yes, you're shown, especially with the summer height.
yeah, you're right. Yeah, no, you're right. Good point. Yeah. You're totally right. Yes. No, what I just said was wrong. Yes. Yeah, exactly. With Hagibis, yes. Exactly. Yeah, I see what you mean. Yeah. Yeah. So here it's like if I took my R34 knots and I took my old model and said, here's what I think Rmax is, and then I fit my old model, then yeah, I get this. Yes. Yeah, exactly. Yeah. So this still, at the end of the day, this enforces upfront that you get Rmax and R34 knot connected in a reasonable way. And so this is where it's possible, though, I guess maybe the way to put it is if I have this and I predict Rmax from my Rmax model for this, I'm gonna guess I'm gonna get an Rmax that's way bigger than observed. And so that's the place where it's like the Rmax model is still gonna generally capture, it encodes the physics of my old model, but it'll at least be better fit to observations because it's empirically based. But this, I'm going to guess this is an outlier case, and it's not. It wouldn't do it. It'll predict our max will be something at really like 150, and then if you fit the Win model, it'll connect to these points, and so it might look okay. It'll look better than my old model, but it'll still, yeah. Like that's where, at the end of the day, to get weird structures, you need an actual estimate of Rmax and R34 knots. So,
But in most cases, it shouldn't be presented. Yeah, and we can live with noisy.
yes, yeah, exactly. Yes, you can live with noisy Rmax, yeah, because it's just the sensitivity. It's almost like the sensitivity to Rmax decreases to 0 as you get to R34 in your new model. Versus the old model, the sensitivity to Rmax is just all the way out. So yeah, it's a good way to think about it. So.
Okay. Any other questions? Okay, so is there any question from online? Okay, so if not, just I'd like to close the seminar by Professor Daniel Chavas. Thank you very much.
Thank you.
Oh, actually, we have a small gift for you. So this is some craft from Kyoto. This is you.
Oh, thank you so much. Yeah, so you said a clef, was that?
Yeah, this is a eraser,
Oh, it's
and you can use it to make this shape.
Really? Okay, that's awesome. Great, thank you.
Okay, another thing is this is a Japanese snacks.
Oh,
for your daughter.
Oh, wonderful. Thank you so much. Thank you. Thank you very much. Yeah. Thank you all for coming. Really appreciate it.
Materials. So
Yeah.
I will send you the recording to at least the participant, and I think he asked me to put it on the website of our group. I will let you know where we have it. And how about your materials? Can I use?
Sure.
Okay, so we can put it on the website. Is it okay? If not, maybe you can be close.
I'm happy to share with you guys. I don't really putting slides. I do it for some teaching, but because I'm trying to remember. I would probably prefer those not just be posted publicly in PDFs if possible.
Okay.
But I don't know if you could send them to everybody if that's fine, or I don't know if that's an option.
Okay, so maybe we can talk
Yeah,
discuss
sure.
later,
Yeah,
but at least
yeah.
I will send you, a visit months. Is it okay?
Yeah, absolutely.
So we can
Totally
discuss
fine.
later.
Yep.
Okay.
Yeah, sure.
So, could you give us some final words?
Sure. I mean, just thanks to all of you guys for coming. Thank you so much for inviting me. It's really an honor to be here, to meet all of you guys, and hopefully maybe chat even a little bit more. Since I'll still am around if you wanted to talk more about different things. I'd love to. But yeah, I mean, thank you so much for inviting me. It was great, and like I said, it was really great timing even for me for my career of all these things coming together. So I was actually kind of excited. In 6 hours, I was like, "Oh, that's a lot." but you can see all these different pieces that I've gotten to be a part of, which I feel very lucky to have been a part of. And so seeing how it all came together, it's been a really nice opportunity for me to put all of these pieces together. So hope you enjoyed me sharing it with you. Love to get more feedback anytime. You guys ask wonderful questions, and it's really helpful to keep thinking about all of these different topics. So it's also just thank you again so much. So appreciate it. Tomorrow afternoon.
Okay, so thank you very much. So this is the end of Typhoon seminar this year. Please help to move the tables and your chairs at the original positions shown in the back. Okay. No, thank you very much.
Yeah.
Okay, very nice. Very excellent.
Thank you so much.
Okay.